Good morning, everyone. Welcome to the third TESS Science Conference. My name is Avi Sporer. I am chairing the SOC and the LOC. What that means is the following. If there is any problem in this conference, anything you don't like, anything you're not satisfied with, the responsibility is first and foremost on me. However, if there is no problem in this conference, if you're enjoying it, if you're enjoying the science and the social interaction with friends and colleagues, then please keep in mind, this is a big group effort. And once I get to the next slide, you will see that it is a big group effort. Okay, that was a little bit way too much. Okay, we have the SOC that read through all the abstracts, graded them, and worked to put together the list of speakers. We have the LOC that is doing all the logistics, and I have to also mention the MIT conference services, which are critical for organizing any conference of this scale at MIT. They deal with all the external vendor and the registration process. There are also the MIT audio video technicians, which you have seen them, but they are mostly behind the scene, coordinating all the presentations. We also have sponsors, the MIT Kavli Institute, or MKI, Nexi, the CFA, Harvard-Smithsonian CFA, and Northrop Grumman, whose generosity allowed us to keep the registration fee from going even higher and allowed us to provide free registration to about 50 participants, which make about 20% of the participants. Those 20% are almost entirely students and postdocs. This is a block diagram of the conference. We have 72 contributed talks, which make for roughly a 40% acceptance rate of abstracts submitted for talks. The SOC has graded the abstract while they are anonymized, meaning we didn't see identifying information about the lead author or any of the authors when we graded the abstracts. We did use information about each of the lead author when we tried to break the tie between abstracts that were just close to the passing threshold, and we use that information in order to increase diversity among the pool of speakers. Speaking about speakers, some technical information. We have lapel microphones like I am using. So if you want to use it, go backstage in the few minutes Q&A during the talk just before you. They will put another lapel mic on you. You don't have to use that. You can use the podium microphone. And there is also a hidden microphone right here. You just take it and walk. Also, there is what is known as a confidence monitor. The reason I'm not looking back is that I have my slides right here. And there will be a timer also there where all the speakers can see the time going down. So you can see how well you're doing with your talk. I want to highlight a few talks or sessions we will have during the conference. Tomorrow afternoon at 4:30 to 5, we will have a talk by a mental health professional from MIT. And in the early stages of planning this conference, the SOC was thinking to use a small amount of time to talk about something else, something that is not directly related to TESS science, but is of importance and interest to this audience. There were a few ideas, and eventually we landed on, let's talk about mental health in academia. And I have to admit that is something I feel strongly about, and I did push for it. The reason is that mental health is something that is not talked about enough, but yet is impacting many, if not most people in our community, and probably all humans. So we need to talk about it more, and we will talk about it tomorrow afternoon. If you want to pre-submit questions for that talk, you can send it directly to me by email or over Slack. Identity of people who submit questions will remain confidential unless you choose otherwise. Wednesday afternoon, we will have parallel sessions. One of the sessions will be here in what we call Kresge Main. The other session happening in parallel will be just beneath us. You walk outside, take down the stairs, walk into a room which we nickname Kresge Little. It's not really that small. It's just much smaller than this room. Parallel to all of that, we will have a live help desk by the TESS Science Support Center from NASA Goddard. And that is a wonderful opportunity for any one of you to go ask the experts about anything within the packages and software and code they have been putting out for the last few years. That will happen in a seating area right next to the posters area, and I'll show in a minute exactly where that will be. Thursday morning, we have the TESS Users Committee, or TAC, session. You can see that we will have an open discussion during that session. It will be devoted broadly from feedback from the community survey and discussions about EM3, TESS Extended Mission 3, which will start, assuming funding from NASA, around September or October 2025. But the proposal submitted to the NASA Senior Review for the Extended Mission 3 will be submitted in the first quarter of 2025, and this conference is timed to jumpstart the process of putting together that proposal. Now, if you did not have the opportunity to respond to that community survey, you have that opportunity today and tomorrow. They have opened that survey just temporarily for today and tomorrow, so you can access it through this URL, this QR code, or just Google TESS Community Survey. It will be one of the very first hits. And I'll leave it for another 1-2 seconds. Okay, some more logistics. We have a Slack workspace for this conference. If you are not there yet, then first check the email you're using for Slack. We may have registered you or added you to that Slack workspace with another email. Also, you might already be there, but did not get a message because you're already in the MIT Slack world. So go check that. Go to this URL, MIT-TSC3.slack.com. If all else fails, ask Mark Hahn. He's the LOC lead on the Slack workspace. Posters. Posters are presented all week long. We have 2 one-hour poster sessions, one today, one on Thursday, where poster presenters are expected to be by their posters to answer questions. It is optional for all poster presenters to upload their poster to Zenodo, which is an online public repository. So that's how they will make their poster public. It will also be indexed by ADS after the conference. We will, of course, have a best poster competition. Participants are only students and postdocs who have opted to be in the competition at the time of abstract submission. And the judges for the competition are non-students and non-postdocs. And that will be done through a simple Google form where you can list up to 5 posters which you deem are best poster candidates. And if you are a potential judge for the poster competition, you have already received an email from me late last night about this. You don't have to be. You don't have to be a judge for the competition. You are welcome. And we are, of course, on social media, on Twitter or X. The handle is TESSCon3, and the hashtag is TESSCon3. We will have a best post competition to encourage people to be creative and interesting in their posts. Again, include this hashtag. We will announce the winners of both the posters and the post competition on Friday. Now, a few more things. We are here at the Kresge Auditorium. Right across the lawn is the Stratton Student Center, where on the 2nd floor, you go up this external stairway, you go into the building, turn left. There will be the room with the posters and the coffee breaks. They are in the same room. That room is called Sala de Puerto Rico, and you'll see all the posters and the coffee breaks. And here is the floor plan of that room. The poster ID will increase from left to right, or more or less from south to north. To orient yourself, Kresge Auditorium is somewhere up here. And the stairway I just mentioned is here. Right next to the room with the posters, there is a seating area, which is free for all of you to use anytime during the week. You can have lunch, sit down with colleagues, talk, or collaborate and work together, whatever you want to do. This is also where we will have the live help desk by the Goddard group during Wednesday afternoon. Options for lunch. If you go to the logistics page on our website, you go down here, there is a link, and you see a list of options for lunch on campus and also off campus, but in a short walking distance. And you can always talk to one of the locals about good lunch options. This event is being recorded, and that is for the benefit of everyone who cannot attend the conference, also for the benefit of you if you want to watch it later, if you're not too concentrated in one of the talks. Speakers who do not want their talk to be recorded, please let me know. Some of you have already done so. We will stop the recording during your talk and restart it after. Now, two more things. One, I want to give a shout out to two of our colleagues who have recently won a very prestigious award, the Kavli Prize, Dave Charbonneau and Sarah Seeger. Especially Sarah, she's been in the leadership of the TESS project from the very beginning, and I believe she's in the room, so help me with a round of applause. This is not the first prize, and it's a very safe bet it's not the last one. Now, really one last thing. Sometimes there are unintended but very positive consequences to things we do, like this conference. So I know about one couple of students who met here exactly, actually, this week, 5 years ago, in the very first TESS Science Conference. And since then, they have fallen in love, got engaged, I think also got married. I will not name names because I'm pretty sure I will embarrass at least one of them, and I'm a nice guy most of the time. So, but if you are single and looking for a relationship, this can happen. Cupid might be somewhere out there. So with this positive note, we will move on. We will start the first session of the week, mission overview, and I'll invite Sam Quinn to chair the first session.
Thank you, Avi. It's my privilege to chair this first session on the TESS mission overview. George, if you can come on up as the first speaker. We will welcome George Ricker, who will give an update on the TESS mission. And I look forward to hearing what's going on and what's going on in the future. Thank you, George.
Okay. All right. Well, it's a real pleasure to be here, and I hope my voice will hold out for the session, but we'll see. There have been two prior such meetings that we've all been had the pleasure to attend. What I'd like to do today is to give sort of a little point backwards, sort of a retrospect, and then mainly talk about things that are actually going forward and going to happen in the mission in the current year that remains of the extended mission 2, and some thoughts about what we may do for the next mission, for the next section of mission. So as far as the retrospect part, this is a sort of a brief history of TESS in a single slide in terms of things that we actually did. There's some smiles of amusement by some of the members of the audience that TESS, the idea related to TESS actually started out at a AAS conference when Dave Latham and I had a conversation to try to repurpose a small satellite that MIT had built previously and it was called Hedges, and that was the idea. And then this actually turned into a proposal that we put together to the Calvary Foundation and to a number of other private funding agencies that we would actually be able to do a TESS-like mission with the resources that they could bring together. And then, the markets changed and some people who weren't quite as wealthy anymore. So we actually said, okay, let's try this out as a SMEX. And then the SMEX was actually proposed in 2008. And then that was not selected. We came in second. The organization that actually finished first was never went on to fly. So I don't know whether that means we should be happy about being second or not. And then finally, it was proposed in 2011 in its current form, and that's what we're all going to be talking about today. So TESS has really continued to enable a very high rate of discovery as a result of what we can see from the papers that the mission has actually enabled. And I think there are three primary reasons for why TESS has been able to enable such a flourishing of results. The first one is we really released the data without any proprietary period, and that was part of the idea from the very beginning. The unprecedented high étendue means that not only will TESS provide a lot of information related to exoplanets, which is in the name, but time domain and multi-messenger astrophysics is really part and parcel of the way that the instruments are actually configured. And then finally, these so-called cameras really are 64 million exquisite CCD photometers, and they have these 4 characteristics that are listed in this slide, and that is really, to my mind, one of the key enabling technologies that we really went for on TESS. Everything related to the instrument has been working flawlessly during this 6 years that we've been operating, and that's really a testament to the skill and dedication of everyone who worked on the mission for the hardware. The publication rate from TESS observations continues to accelerate. This is a bar chart that shows that we're approaching 2,000 publications. In fact, in 2024, we've actually gone beyond that. And most of these are related to general astrophysics, but there are, 1/3 of them are related to exoplanets per se. And here's a way to actually look at how TESS is done. The cliche is TESS punches above its weight compared to 4 other NASA missions. And as you go across on the x-axis in time, you can see when TESS turned on in the 2018. And the notable thing is the slope that in the publication rate that we've achieved. In fact, if you then extrapolate this to 2024, to the date that we have right now, there's more publications. And if you take this year's rate through today and you extrapolate to the end of the year, we can expect to have about 850. So the bottom line is that we're approaching the Hubble publication rate in the early part of the next phase of TESS extensions, we hope. Okay, now, how does TESS manage to provide all this information? First of all, it has an enormous field of view. It covers a little bit more than 5% of the entire sky at any given time. And if you actually look at what a TESS camera sees, this is one camera out of the 4. It's an area on the sky, 24 degrees on a side. And so what's shown here is just one of the 4 cameras. The moon would fit in, 10,000 moons would fit in this. The Kepler field of view was 100 square degrees or 105 square degrees, and it fits within one of the CCDs. And then if you look at some of the other initiatives that are ongoing, this is where ZTF stands. This is what LSST's field of view would be with approximately 10 square degrees. And then this is the wide field imager for Roland. So the grasp, the étendue of TESS is really the secret sauce that makes the mission behave as it does. And then with the 200-second exposures and the full frame images, we're able to produce more than 10,000 successive images with 200-second resolution every observing sector of 27 days. So that to me are the two of the things that have been so critical in the success of the mission. Now, there's also been a progression in the science data downlink capability that we've been able to configure for successive mission extensions with TESS. The cartoon that's shown now shows how TESS was configured in the prime mission for 2 years. There were 2 contacts near perigee, and we had 30-minute FFIs. Then in the next extended mission, we reduced that time to 600 seconds. And then in the current extension that we're operating on, the FFIs have been reduced to 200 seconds. And we've also introduced 20-second targets as well as a prompt methodology called TICA that Michael Fassnow was largely responsible for, working on that with Chris Burke. And then for the upcoming mission extension, we anticipate that we'll be able to provide these same modes. And then in addition, we're talking about having 2-second targets as well as some real-time samples that are associated with an interval when we normally achieve only engineering data. This is the so-called HASO section that's shown, I guess, right here, these 4 contacts. Okay, now, so then if we consider the sky coverage in the successive mission phases, Roland Vanderspek will be talking about some more of this in greater detail than I will. We've achieved the coverage of the sky that's shown in these maps on the right-hand side, and there's some cleanup on some of the gaps that are going on in the current extended mission. But all in all, the sky coverage is better than 97% at least once, 84% twice, and about 2/3 of the sky at least 3 times. And that'll be the case after September 2025. One of the key things that has enabled TESS to have the success that it has was this choice that we made of a P/2 lunar resonant orbit. Now this orbit is stable. It's stabilized by the Kozai-Litoff mechanism, and that was something that we actually planned. And this chart actually shows the changes that take place in perigee, and those oscillations are related to the effects of Jupiter in a minor way, the moon, and the sun as well. And this stable orbit behavior is anticipated for about 100 years. And if you actually see just what's shown here for 25 years, then these are where the missions that we've had so far with TESS since the launch in 2018 fall. And then for another question often comes up is, well, how long might TESS last? It has propellant for that's needed for maneuvering, and that is something that works out to be certainly far greater than 100 years, because there's 29 kilograms left, and it's one gram per month. So you can do the arithmetic. It's a long time. It's more than anybody in this room will ever think about being around for. So for the 122nd and 22nd target utilization. This is a table that Roland is actually going to discuss in more detail in his next talk. But the one thing I wanted to focus on is that the director's discretionary time slots have been dramatically undersubscribed. And the number of DDT programs, for example, in EM2, there have been 28 so far for the 22nd mode. And the thing I'd just urge everyone to be aware of the fact that this opportunity exists. The only thing you have to be sure of is that the proposals have to be submitted 6 weeks or so before the start of the sector in order to be scheduled. But it's very little overhead in terms of actually doing this, and the directions are on the MIT website. Okay, in terms of where we actually stand today, this is a sky map that gives the status that we have for the TESS objects of interest. These are exoplanet candidates. There's 543 that are on the exoplanet archive that was updated just in the last few days. That's 543 handily beats the TESS mission requirement by an order of magnitude. And there also have been more TESS planets with measured masses and radii than was the case for the Kepler mission and K2 separately. So the follow-up observing program, Dave Latham will be discussing. This has been an incredibly successful initiative and has involved the organization by Sam Quinn and Karen Collins and the group at CFA, and it's just been a marvelous success, and you'll be hearing a lot of that as the program goes on. One other thing is that TESS data are in high demand by the community in other ways that have reflected the volume of data that we've had to deposit and have made available at this Space Telescope Science Institute MAST archive. The users have been downloading this data at an incredible rate. This is a plot of the holdings versus the data demand. And the two little dots that are encircled in this are those for JWST and TESS, and the one that's sort of down around 5 o'clock, that's Hubble. So it's been really successful in making the data available for the community. And then for the high-level science products, the HLSPs, this is the area of this diagram where they actually lie. And the Quick Look pipeline and the Goddard Eleanor Light programs and the TESS-SPOC and the TGLC, which was a format that has come into recent use, is another way in which we can exploit the data. And this is another map that actually shows the download rate, and these are the 5 forms of the data that have been most attractive to the communities. Okay, now TESS is enabling a broad range of non-exoplanet astrophysical discovery areas, and the check marks on this mean that there are TESS results that have occurred in every one of these topics during years 1 through 6, and we'll be hearing a lot more about that as the conference goes on. And then just looking ahead, another thing is what might we do with future missions that are coming up. Plato certainly is going to be an important contributor to future progress, and this map shows the so-called LOPS S2 field near the south ecliptic pole for EM, and if you look at where TESS could look, this has not been set during that period of time. This is the way it would actually look if we were to observe in 55-day sectors. If you wanted to work with shorter sectors, you just have to make more maneuvers, but basically by turning this diagram, you can see that it's possible to cover the entire 7,000 plus square degrees that encompass the field that's been selected for Plato. Now, the extended pointings at the north ecliptic pole, or the south, in the case of Plato, the south ecliptic pole, can have another series. There's a series of advantages that I think will be considered by the TUC and in discussions that we have here that are shown here, that are shown in this list. And there are a number of possible plans that are in discussion, and there have been suggestions already from the community as to how some of these things might be worked out. The south, one idea might be to do the south ecliptic pole in cycle 8, and then the north ecliptic pole to a much deeper degree, while Plato is observing the south ecliptic pole, and the missions would be complementary in that respect. And then the other thing that we're talking about is to do more frequent downloads of the TICA-derived special intervals to support other missions. That's already been done for things like gamma ray bursts as well. So this is a timeline that shows where we are. This is where we are in extended mission 2 in terms of the other programs that are underway, and this is where we will be with regard to those programs. And especially in EM3, the Rubin Observatory will come into its own. There's going to be another series of observations from LIGO. Ultrasat is going to launch, and of course, there's Plato and the work that's going to be going on with the ground-based extremely large telescopes, and of course, Roland. So the other thing I'd like to end by showing this slide of the members of the first TESS Users Committee. Most if not all these people are here, and they're going to be a vital contributor to our planning in the future, and we welcome them and plan to provide as much information as we can to enable their work. Roland is actually going to give a briefing for the Users Committee meeting on Thursday that's actually related to some of the things that we can and cannot do with the satellite from the point of view of practicalities. And so I'd like to stop at that point and be happy to answer your questions.
Okay, we do have time for questions, and there are a couple volunteers running mics. So if you'd like to raise your hand, we'll get a mic to you as soon as we can. I'm sure there are questions about what's happening with the mission. Yes, one in front here.
Hi, thank you so much for your talk. You mentioned the TICA prompt product a couple of times. I'm not familiar with that. What is that useful for?
Could you repeat the thing you said?
TICA prompt, what is that? TICA? You mentioned it as something that's been added to some of the cadences in recent downlinks.
The distortion in the mic is making me hard to understand.
The TICA products?
TICA prompt.
Oh, TICA. Okay, that's a form that's from the full frame images. It's a pipeline that was developed largely by Michael Fassnow and Chris Burke. Basically, it's a way to provide the calibrated full frame images in approximately 1 to 2 days after the receipt of the data from the downlink. So you can it's called an HLSP plus on the website at MAST, and you can download the images and use standard. They're in a standard FITS format, and it's based on 200-second data. It's a very useful product that a lot of people are actually relying on. It was introduced earlier in EM2.
Thank you.
Any other questions? And okay, one back there. And when you ask your question, I should have mentioned at the start, could you please say your name and your affiliation?
Tara Featheroff, UC Riverside. So you keep mentioning about the addition of new modes, which is awesome, but what kind of sacrifices need to be made to add new novel modes, such as additional data links?
Well, I think I understood your question. If the question is, what do you sacrifice if you add these modes? So far, the things that we've introduced don't really sacrifice anything, because if you wanted to use the 30-minute data or the 10-minute data, you can just basically add together the 200-second data. So 200 seconds, 600 seconds, 1800 seconds. So those integral multiples are easy to achieve with the data. As far as the other modes that have been introduced, the 20-second data has been particularly valuable because it actually it affords the possibility of not relying on the cosmic ray mitigation, as we call it. Mitigation means you correct for cosmic rays that produce false events. They look like stars, or I mean, they can be a variety of forms. Currently, that's done on board for the 200-second data, but with the 20-second data, you don't have that, and you can do it on the ground. And the implication from that is, and this has been well documented, is that the photometric precision that you get is significantly better for really bright stars. If you're talking about things that are 6th, 7th magnitude, that's something that you may want to do for photometry. That I'm sure can be discussed. The people who originated those tools are in this audience, and that can be covered in questions or any of the special sessions.
Okay, I think we're going to have to cut off questions there and move on to the next speaker. So thank you again, George.
Yeah, thank you.
And if there are additional questions, you can put them, I believe, in the Slack, Avi? In the Slack, and the speakers can respond to those afterwards. Please address them to the speaker you'd like to ask the question. Our next speaker is Roland Vanderspek, and if history serves as any indication, he's going to tell us a little bit about operations, mission operations.
Yeah, I get the good stuff. Good morning. Sorry, I've got to get myself oriented here. Yeah, I'm going to talk about mission operations, mostly current stuff, a little bit of a forward looking to EM3. I'll cover the standard stuff, the current status of the instrument and the mission, and talk about the pointings and target selection for year 7. If time allows, I'll talk a little bit about cosmic rays, because that's fun stuff. So I love this particular slot for speaking, because I get to stand up here and show a slide that says everything's working just fine, thank you. So the cameras are fine, the focus is stable, all of these things. The CCDs are not showing any major signs of degradation. Command uplink and downlink works well in general. There are hiccups, but we know how to deal with them. And the whole process of getting targets on the sky and getting operations going is pretty routine. The science operations are going well in general. There have been a couple of hiccups, and I'll talk about a couple of the hiccups, but we have collected 98.5% of the available data so far in the mission. Specifically about the spacecraft, again, it's in good health. There was a recent analysis done that shows that the solar arrays are generating less current with time, as you would expect, but there's plenty of current to keep us going till 2050. The same analysis showed that the battery capacity is dropping with time, as you'd expect, but we don't use the batteries except in eclipse. And looking at the eclipses for the next couple of decades, we're fine until a particularly nasty one in 2037. But if we're funded in 2032, we can also push the spacecraft around to avoid that a bit. And as George mentioned, we have sufficient propellant for 100+ years, so that's not an issue. One thing that we are looking at is what we call a limited lifetime object. It's this micro inertial measurement unit, MIMU. It has a ring laser gyro in it, and that laser can, well, it has a limited lifetime. So what we would like to do is take it out of the attitude control system algorithm. The work on this has been done by Northrop Grumman, and it's been ongoing for a year and a half or so. It's under continuous test. We are going to test a flight software patch, 510. The test gang knows when you say 510 what we're talking about. 510 ACAS patch. We will have to do some tests of 510. A lot of it is being done on a simulator, but it's nothing like real life. So we will have to steal a little bit of science time to do these tests. We had a simple test for wheel calibration just the day before yesterday. That went fine. You lost 8 hours of science data. Sorry about that. We will soon come up with a test. If this calibration works out well, the next step is to do a 2-day test of patch 510, which means we will have a different attitude control system behavior for 2 days of a sector. So instead of your spots looking like this, they might be slightly elongated. We'll challenge you to see whether you see a difference. We'll do our best. The Spock will do its best to make sure that the differences are not noticeable by you. If that works out, we'll do a whole sector. So it'll be a whole sector of running 510. We will, as we go along, we'll assess what the quality of the attitude control system mods has been. So I spoke of bumps in the road, and one of them has been missed contacts. Excuse me a second. And I just wanted to walk you through what's going on there because you lose data in some situations. Now, as George pointed out, current operations have us downlinking data at perigee and at apogee, but that wasn't always the case. We used to have 2 contacts at perigee. This was before we went to 200-second FFIs and had so much data to downlink. The advantage of having 2 contacts is that if the first one fails for whatever reason, you have the second one there to back up as a backup, and you can downlink your data. The disadvantage is that you lose 12 to 18 hours per orbit between the contacts. So when we went to the perigee and apogee downlinks that George mentioned, we regained those 12 to 18 hours per orbit. So it's a day per sector of extra observing time. But there's a little bit of risk if there was an issue with the downlink. So I've got no, wrong button. So I would just want to explain this graphically. We have a solid state recorder on board that has 196 gigabytes of space. The flight software in the instrument is commanded to stop collecting data from the sky if the SSR gets to 97.6% full. And you can't restart it unless you've emptied it below 95%. So in a typical half orbit between apogee and perigee, or between perigee and apogee, we fill the SSR to 50 to 55% full. It's a little bit more if there's more scattered light. But in normal operations, we fill it at 55% full. We downlink the data, everything's cool. We remove the data from the SSR. So it's back down to 0 or close to 0. If a contact fails, we don't downlink those data. We don't know what those data are called. We're not going to remove those data from the SSR. So another half orbit of 55% will cause you to overflow and exceed the 97.6% limit. So in that case, the instrument will stop collecting data at 97.6, and you'll lose a few hours, or more than a few hours of observations. Now, this hasn't happened a lot. There was an event in May of last year where we lost 17 hours. There was an event last December where we lost 51 hours. And then there was April of 2024, which I'll get to in a minute. It's a story to itself. But we are trying to improve this. We're trying to improve how much data, we're trying to minimize how much data is lost if we lose a contact. So as you know, the science data are compressed on board to roughly 3.5 to 4 bits per pixel. If there's more scattered light, it's lower. The compression is higher. Bits per pixel is higher, compression is lower. So we're looking into that, how to improve that. And the main thing we're looking at right now is the possibility of just running gzip on the spacecraft processor. I'll note that the data handling unit for the instrument is basically just a Linux box. So let's put gzip on it and run it. It's very comfortable to look at the code and the processes on the DHU. So we're testing various scenarios. How frequently do we want to gzip? Do we want to gzip everything? It's all a work in progress at the moment. And I wanted to remind you, and this is sort of a foreshadowing for the TUC session on Thursday, which is going to be really fun and really important. I hope you all show up. The FFIs take up 85% of the SSR, of the data that is collected. So adding a few targets or reducing a few targets doesn't have that big an impact. If you increase the number of targets, basically what you're doing is increasing the amount of data that you might lose if we miss a contact. So apparently I've been signed up to give a talk about that on Thursday, so I'll go over that again. Okay, so you may have noticed that there was a bit of a data gap in April in sectors 77 and 78, and I thought it'd be worthwhile just to step through the timeline of what happened there. On April 1st, there was a missed contact. Okay, we understand that. We understand that we would lose some data. We were expecting to get the data down on April 8th. Unfortunately, when the spacecraft came around on April 8th, it was in safe mode. So the SSR was full, and we can't talk to this. The spacecraft was in its safe contingency mode, where it's pointing the panels at the sun and the instrument is safe. It's a very safe state. But we weren't able to downlink data. We've gone through standard procedures to get the spacecraft going by April 11th, but the SSR is full, so we can't take any more data. On April 16th, we downlinked the data successfully and started science operations again. On the 23rd, we downloaded an orbit's worth of, half orbit's worth of data, but the spacecraft went into safe mode at the end of the contact. This caused a little bit of a pause because we weren't really sure what was going on. So there was a bit of time where, quite rightly so, we didn't do anything. People went off and thought and talked. And by May 3rd, the problem was understood. Tests had been performed to make sure that the hypothesis that we had about what had happened was correct, and we returned to science operations. So in total, there was partial data loss in orbits 161, 162, 163, 3 days, 7 days, and 11 days respectively. The NASA was very good about letting you know what was going on through a series of press releases. But the key takeaway from this is that we understand what happened, and it's not going to happen again, short version. So in case anybody was concerned. So I'll move on to year 7 pointings at this point. As you may know, our observation plans for 5 through 7 were to use 5 through 7 to finish the south and start the north, or finish the north, start the south. We're in year 6 now, do a little bit of ecliptic and then some northern sectors. And then in year 7, finish the northern scan, do some ecliptic, and start another southern survey. And on the right is a nice plot that Chris Burke put together of how frequently targets have been observed in the course of time. On the left is the image that Luke Bauma put together for us. Luke has a strange sense of direction, so I have to flip to make it match. But the key issue here is that we've got I forget the number, but I think it's 90, not greater than 95% of the sky covered by the end of EM2. And this hole is due to a region of scattered light, high scattered light, which I call the zone of avoidance. I don't think anybody else calls it the zone of avoidance, but at least I know what I'm talking about, and you'll have to live with it for this talk. So the zone of avoidance is a region of the sky where the Earth is where the Earth is seen at TESS orbit apogee. Now, if you look at the plot on the right, this is a straw person diagram of what a 13-sector TESS year would look like. These are elliptical orbits, roughly the same, the right size. The small blue triangles are the pointing direction of TESS. It's always anti-solar, as you'll notice as you go around the clock. This big blue sector triangle denotes a sector. And you'll see that there are times when the Earth, which causes the bulk of our scattered light, is in the field of view when we're looking anti-solar. So you'll see that regardless of where you are on this, in the course of the year, the Earth is always going to be in the same direction, the same rough celestial coordinates, regardless of where you are in the year. And these orbits are considered bad orbits. They're going to have higher scattered light than these orbits where the spacecraft is pointing away from the Earth at apogee. And apogee is important because the spacecraft moves most slowly at apogee, therefore the Earth drifts through the field more slowly at apogee. So just to make this a little bit more visible, first off, the figure I put together in 2015 using PowerPoint turns out to be not completely accurate. But oh, this is unfortunate because this was the most fun part of my talk. Somebody start my, oh, good Lord. Don't look. I blame Avi. Oh, yeah. No, I think it might want to be doing something. Yay, okay. No. It's a bummer. Those are good animations, too. All right, well, I'm going to give this 30 seconds, then I'm just, you guys are just going to, you lose, sorry. Anything I can do, Avi? Besides stand here awkwardly, I'm good at that. Okay. Well, if this happens to wake up in the course of the next 10 minutes, I will go and show you the cool animations, which I spend a lot of time putting together. So the key here is that because of the precession of the TESS orbit, which you would have seen in the cool animation, the zone of avoidance, which for the first 4 years of the mission sort of lingered at where Y4 is on this map, and which is the reason why we raised the fields of view in sectors 14 through 16, 20 through 24 through 26, and a sum of year 6. That will start to move because of the precession of the orbit. And it will move from where it is at Y4, which indicates year 4, across the field, and will settle in where Y9 is, which is sometime in the middle of EM3. So this motion it's hung out here for 4 or 5 years, and then it quickly screams over to where Y9 is. What the cool animation would have showed you is that after settling here for another 5 years, it would quickly move back to roughly where Y4 is. I guess that's Kozai. But the key for this is that we had to raise the fields of view to date to be able to do decent science here because the Earth was screwing things up there. But once we get to year 8, year 9, observations in this part of the sky will become possible again. And you can see it here. No. We had to push the fields of view north in year 6. So we'll be able to close that gap in EM3. And we'll get that little bit of the ecliptic in year 7. So again, foreshadowing a bit the TUC session on Thursday. What we've done so far, based on the requirements for the observations for the mission. Thank you, Sam. We've been pointing north, south, and along the ecliptic, but it turns out there are a wide range of alternate observations modes, which I'll get into on Thursday, which can lead to interesting pointing scenarios like, let's just do the middle latitudes and to heck with the continuous viewing zone, or let's just look at one spot of the field and screw the rest of the northern hemisphere. So we'll talk about that on Thursday. Targets, you've seen this slide. Typically, I show the same slide every year at science meetings, and it's basically the same thing. We create an exoplanet CTL based on all the targets that weren't seen in the first few years of the mission. And usually I have something at the bottom saying, oh, there's plenty of room. Given the cycle 6 GI allocation, we'll be able to observe everything. Unfortunately, as Christina will get to in a couple of talks, there's a lot of extra targets this year, and we're not necessarily going to get to all the targets that were proposed to GI, but Christina will talk about that. And again, we'll talk more about this on Thursday. The last little bit, oh God, this is an animation. Is it gonna work? Yes. As George mentioned, cosmic ray mitigation is done on the ground using the 20-second data, and they kindly store what they subtracted from all the pixels when they saw a cosmic ray, so you can reassemble the cosmic ray tracks. And this is one 11 by 11 postage stamp, 20-second data, 11,000 cosmic rays. I don't remember the exact number. But the nice thing is that you can use these tracks to calculate the cosmic ray flux. It's not as easy as just adding everything up for reasons I can get into later. But we have been able to put together a map of the cosmic ray flux as a function of time. Now, all these spikes at the top, ignore those for now, because those are due to scattered light or high jitter regions. We're still working on a way to get that out of it. I just sort of do a little chi by eye thing here. It was flat at the beginning, and then it stopped being flat, and now it's flat again. And this correlates well with solar max. As the activity at the sun increases, the heliosphere expands, blocking off the galactic cosmic rays that are coming in. They're usually down by roughly a factor of 2, which is what we're seeing here. And this correlates with sunspot numbers that are being measured by ISIS. So that's a fun little story, and the animation works, so that's a bonus. So in summary, everything's working fine, but sometimes stuff happens. The key subsystems of the spacecraft are going to be good for many years. We're looking at ways to improve the things that we can, and we're very much looking forward to discussions of the of EM3 in the TUC meeting on Thursday, if I hadn't mentioned it. Thank you.
We do have time for a question or two. I don't know, Roland, if you want to see if that slide is working now.
Well, that's gone, so. Oh, no, thank you. Appreciate it. No questions, cool.
Any questions in the audience?
I'll just find the animation then.
Hi, Roland.
Hey.
I'm Damoto from the University of New Mexico. So what did happen in April?
There were two things. A test of an engineering test was slightly misconfigured, which has caused us to go into the first safe hold. And that test is the one that was just done again 2 days ago, so that's all cool. The repercussions of that test was that a valve that controls the flow of propellant to the thrusters closed, and it wasn't noticed. And you may know at the end of every downlink, we do a momentum dump where we change the speeds of the reaction wheels by applying a little bit of propellant. The first time that happened, there was enough residual gas between the valve and the thruster that we could actually do the momentum dump. But the second time, it was trying to start the car with no gas. And the spacecraft is pretty smart at noticing those things. This is taking too long, it said. Let me get into my completely safe mode. One thing about this spacecraft, when something goes wrong, it gets into its safe mode right quick. And it's very nice. So that latch valve was opened and everything's cool. And the reason for it being closed in the first place has been addressed. Does that get close to answering the question? Okay.
Good time for one quick question here. Sarah?
Oh,
I'm
hi,
just
Sarah.
curious about what is the limiting factor for tests? You mentioned the guidance box, you mentioned the batteries, and you also said you have workaround for those, and it's not the fuel. So what is the test limiting lifetime factor, like subsystem?
You mean besides money, I would assume?
Besides money, besides money.
That's a really good question. I'm probably not qualified to answer that well. I just know that we're addressing what we can. There are single string items on a spacecraft of this type. So there are single point failures, but I couldn't speak, unfortunately, to lifetime. Sorry.
Okay, let's thank Roland one more time. Thank you, Roland. Our next speaker is Dave Latham, who's going to talk about the TESS follow-up observing program.
When we started thinking about how to follow up the discovery by the TESS satellite of candidate transiting planets, we relied heavily on the experience with Kepler and K2. So I'm going to subject you to my history of what we learned from Kepler and K2. But I didn't want that to be K2. That's what I wanted. So this history starts with the first transiting planet, HD 209458, 2 back-to-back papers in the APJ letters in January 2000. That's actually a very important event because we were just in the process of submitting the final proposal after the concept study for Kepler, a month after those 2 papers came out. And we like to think that it had an impact on the selection of the Kepler mission because lo and behold, there were transiting planets that we could hope to observe, and lots of them with the unexpectedly short periods, 3.5 days in the case of 209458. So the Kepler mission was selected for implementation. It was a Christmas present in 2001, launched on my mother's birthday in 2009. And there was reluctance by mission managers to release the data. There was a long proprietary period because of that paranoia that there might be premature announcements that would later be shown to be false. And that led to pushback from the community. And the reaction was to shorten the proprietary period. And that convinced us, if we didn't need to know with Kepler, also with K2, that we should have no proprietary period with TESS. And there were opportunities for community members to join the Kepler mission by submission of proposals to a solicitation from NASA. And there was encouragement of community involvement in working groups. that could join together with the Kepler team. And all three of these strategies we adopted for the TESS mission. And then we get to K2. Now we get to K2. You have to massage this button? Yes, you don't want to hit it too hard. So you all know the story about the second of 4 reaction wheels failing in May 2013. And a couple of smart young engineers at Ball Brothers in Boulder figured out a way to track along the ecliptic. We couldn't track in the original Kepler field, the fine tracking that was needed for the terrific precision, photometric precision that Kepler was giving. And that would require anti-solar pointings along the ecliptic and use thrusters for corrections. It was an unstable equilibrium. It would gradually start drifting off and you'd have to kick it back with the thrusters. And there was minimal funding and therefore there was no proprietary period and minimal funding and minimal support of a science team. And so the reaction was that teams grabbed the lowest hanging fruit and rushed papers to publication, often half-baked papers, often duplicating other papers. Chaz called it the Wild West. And after 18 campaigns of 3 months each, the thruster fuel ran out in summer of 2018. And miraculously, TESS launched just in time to start science operations in summer of 2018. So we brought a lot of the expertise that we had learned from the Kepler and K2 into the TESS follow-up observing program working group. So our goals, get the best science. Well, we initially emphasized exoplanet science, but of course we want the best science from all kinds of astrophysics. And we certainly wanted to avoid the Wild West. And we wanted to meet the level 1 science requirements, 50 planets smaller than 4 Earth radii, with masses and radii. And we wanted to harness the resources around the world to get those observations. And we wanted to encourage people to work together. So communication and coordination would be important, especially of publications, to minimize duplication of effort, get high quality papers. And personally, I wanted to promote and protect participation by early career researchers. And at this point, I want to acknowledge the critical role played by ExoFOP TESS at the NASA Exoplanet Science Institute. That is an effort to bring together and serve all the useful information about the results for TESS objects of interest, the candidate transiting planets. It has the basic information for every star in the TESS input catalog, 1.7 billion roles, and individual pages for the candidates, not just from the mission, the TESS objects of interest, but also the community objects of interest. And eventually includes all of the Kepler objects of interest and K2 candidates so that you can match up the data, for example, to improve ephemerides. And it's a repository for all of the TFOP working group observations. And most of those observations are posted without a proprietary period, although in some cases where it makes sense, you can ask for a 1-year proprietary period. And it supports the facility for entering observing notes and even interpretation, discussion of what kind of configuration a particular TOI might be. And perhaps most importantly, it was responsive to users. The equivalent thing that was done for Kepler was designed from the top down. The ExoFOP TESS was built from the grassroots up to respond to what everybody was hoping they could get. And I should also note there's an important role for the STSCI providing through MAST the test data products themselves. But the two facilities complement each other very well if you think about it. So how's my time going? Well, I'll go through this very quickly. Most of you have seen this before. I checked the list of people attending the conference and counted more than 90 members of the TESS follow-up observing program working group. So I'm preaching a little bit to some of the choir. SG1 is the largest effort by several measures, led by Karen Collins in the front row here. A lot of the work is to identify eclipsing binaries that are contaminating the TESS photometry because the pixels are so big, 21 arc seconds. So seeing limited photometry can get down 1 or 2 arc seconds. It's nice if you can confirm if a transit is on the target star at that better seeing resolution. But of course, the ground-based photometry won't have the limiting precision that you can get from space. So you can confirm that the events are on from a giant planet are on the target, but not for the really small objects of interest, companions. And quite remarkably, Karen and now Crystalline working with Karen review all of the light curves that are submitted by the community. And not every community member does a really good job of it, but a good job gets ending up on ExoFOP because of that review. Quite amazing. Second subgroup is recon spectroscopy, led by Sam, 2 minutes. And 2 more. Oh, we skipped over something. Well, you just have to imagine because I'm running out of time. There's additional working groups, single transit planet candidates, led by Deanna, and transiting brown dwarfs, led by Theron. Going to have a special session on Wednesday in the afternoon on the work going on now, and that's a new working group just in the last year. 543 confirmed test planets in the exoplanet archive. Compare that to 322 from Kepler, mostly fainter, much harder for follow-up. 106 from K2. These are the prime targets. The TESS confirmed planets are the prime targets for JWST because they tend to be brighter. Of course, it's the smaller targets that you don't get from the ground-based bright targets. And many papers led by early career researchers. I like to think that we're training a whole new, we see the training of a whole new generation of exoplanet experts. And I would call it a successful social experiment in widespread collaboration. It's amazing how well the community worldwide has bought into this effort to get the best results, the highest quality results, and get proper credit to people that deserve it. So I'm going to end with a couple of figures prepared yesterday by Sam, so they're obviously up to date. Between August 2021, which is nominally the end of the prime mission in terms of meeting level 1 requirement, 2 years on the sky and a year to get our stuff together. And that's 65 test planets published. And on the right, you see right now, 146. Isn't that interesting? It's every 3 years, we're getting about 65. The quantity, will this go on forever? Well, maybe not. So I'll let you gaze at those results, which I find quite remarkable, while we go into questions.
We do have time for a question. Yeah, David.
Ciardi.
Hi, this is David Ciardi. I'm next slide. So you missed one very important piece for the success of the TFOP, and that is Dr. Dave Latham. This whole thing would not have worked if it had not been your ability to work the politics and the foibles of our community, to work through the lessons from Kepler and K2 to help build the collaborations. And so when you give this talk, you need to add your name to the bottom of that or the top of that list next time you give this talk. Anyway, from the whole group of us that have been doing this for Lord knows how long we've been observing, just thank you.
It wasn't a question, but I'll allow it.
You're not supposed to use cats in public for the last couple of days, but this work was a little bit like herding astronomical cats.
Understood.
I'm sure Dave would be happy to talk follow-up with you throughout the rest of the week. But let's thank Dave again, and we'll move on to our next speaker. Okay, our next speaker is Christina Hedges, who's going to give us an update from the TESS Science Support Center at NASA Goddard.
Fantastic. Do we have a clicker? While you go find the clicker. Green event. Okay, I thought this was a walkie-talkie. Hi, everyone. My name is Christina Hedges. I'm the lead for the TESS Science Support Center, and I'm going to give you a really quick update from the TESS Science Support Center. To start with, gently click the walkie-talkie. No. This green button? The other big green button, got it. Hi, you'll see these smiling faces here at the meeting. This is the TESS Science Support Center based out of NASA Goddard. We're here to help you use the TESS data. We're here to do anything that we can to make it so that the TESS community can use the TESS data. All these smiling faces are going to be here, and we'll be staffing a help desk in this meeting, which Avi has introduced. We'd love to see you there. We're very happy to help you with any of your TESS-related problems, even if it's problems with software that we've put out. So what does the TESS Science Support Center do? So we do two main things. Firstly, in this big blue box, we do anything we can to support you, which means maintaining a help desk. We build different tools to help you use the TESS data. We build new products for you to help you detrend the TESS data. We create tutorials, run workshops. You can find us at the AAS. You can visit our website to find out more about what we're doing. And then inside that box, we also run the TESS GI call. The TESS GI, or General Investigator Call, is there to give you access to funding to do your research. And each year we give out lots of money to the community to enable TESS science. So the TESS GI program is here for you. We give out TESS targets, which Roland has mentioned, which means that you can propose to have targets added to the list to get 2-minute and 20-second data. We give out funding. We give out $3 million every year to the community to do TESS science. And we give out small amounts of time of other telescope time. So we give out a little bit of Swift time and a little bit of NISA time during the GI call. So if you're interested in X-ray astronomy, you can also get a little bit of time to do that. Proposals are short And their phase 1 proposal is due without a budget, which largely means that you don't need your institute's sign off to put in a science proposal to the TESS-GI call. TESS is a community mission. It's led by community science. We really want to support you, and we want to support varied science. I'm going to tell you a little bit more about whether you're eligible to apply for this, and I'm going to tell you a little bit more about what we got proposed this year. Please apply for funding. Okay, can I apply for funding though? I made this handy dandy flow chart to help you understand if you can apply for funding. First off, almost certainly, in some way, if you're a USPI, there is a way for you to apply for TESS funding. If your proposal uses only TESS data, then you can potentially apply for funding. You come down this track, do you only use TESS data? If your proposal benefits from new TESS observations, you can put in a TESS-GI proposal, you land here. If your proposal doesn't benefit at all from any new TESS observations, then you get punted down here and you have to go into the ADAP proposal call, which is Archival Data Analysis Program. If your proposal would use some other data, which would be Hubble data, you should probably go to the Hubble proposal call. But if you want to use some nicer time Fermi data, if you want to use Swift data, you can come back to the TESS-GI proposal call and do a joint proposal. You can get that UV or X-ray data along with your TESS data. If you're not going to use new data, but you are going to do ground-based observing, which supports TESS, you can come in and do a TESS ground-based proposal. We'd love to see those. You don't have to have new TESS data if you're going to do a ground-based proposal. If your science fits in any of these categories, please apply for the TESS-GI program. We have 4 different kinds of categories, which I put here on a flow chart, which I won't step through, but we have mini proposals. Mini proposals are there so that you can just do a really quick 2-page, please put this target into your target list kind of proposal. The barrier for entry is really low. You won't get any funding to analyze the data, but you can put in this proposal so that we will add things to the target list. That includes 20-second targets, which are oversubscribed. You can put in a small proposal. A small proposal is for targets and funding if you are from a US institution. Small proposals, if you are putting in thousands of targets or you need an amount of money, which is something like, I need a student to come and look at this data, then you might want to put in a small proposal, which, oh rats. Oh, good. You'd put in a small proposal. If you're looking at something like, oh, I kind of need a postdoc to do this amount of work for something like a year, then you might be putting in a large proposal. Large proposals are 6 pages instead of 4. You can get large numbers of targets, large amount of funding. This is $250,000 of funding for you to do your science. We do solicit key programs. They weren't solicited this year because of EM3 coming up, but key programs are multi-year programs where you can have $250,000 each year for multiple years to do really large programs that benefit the community greatly. Okay, so what do we get this year? So cycle 7, we had hundreds of thousands, more than 140,000 targets requested in cycle 7, and 35,000 of those were 20-second targets. This is actually more than the budget, as Roland has already said. This means that the community want more targets than TESS is able to give, which is fantastic because it means that people really care about TESS targets. People really want this TESS data. We will be giving out $3 million in total of awards for TESS science. This includes previously selected key programs, which are those multi-year programs. At least $500,000 is going to be given to ground-based support programs, which mean programs that are using that ground-based data to support the science and TESS, whether it's planets, stars, extragalactic. We had 123 proposals submitted, and we're currently in the selection phase for these proposals. You are going to hear more soon, but you can come and ask me and bother me and tell me, please, please tell me more, all meeting if you like. I want to give you some submission highlights about what we got. This is for, no. Love this pointer. Please. No. That was like, there we go. This is the proposal year, and you can see this is the amount of dollars that we get requested. We get requested about $9.5 million worth of science every single year, and you can see that there was one year that really took a hit. We think this is probably due to the COVID-19 pandemic, and we're pleased to see that the requested dollar amount has bounced back. Over on the right-hand side, we have the total number of proposals, which similarly follows the amount of money that was requested. And you can see that we're only able to select about a third of proposals because we ran out of funding before we ran out of really awesome science proposals. This gives you an idea of what sort of science we're being solicited for. This is self-identified. So this is a STARS proposal if the proposer thinks it's a STARS proposal. But people are self-identifying mostly as STARS proposals being solicited for TESS. Then we have a really big chunk of exoplanets, which is TESS. TESS is sort of bread and butter, and then some additional extragalactic, solar system, and a few other proposals that are sprinkled in here. We love to see these unusual use cases for TESS data. We love to see extragalactic and solar system science done with TESS. So if you have ideas to do that science with TESS, please consider proposing. Selections are going to be coming out soon. The deadline was on March 21st. Selections are going to be coming out really soon. Please look forward to TESS cycle 8 in spring of 2024 for putting in proposals for science funding. Okay, in this meeting in particular, I really wanted to highlight that I would love your feedback about the TESS GI call. I would really like to know how this is benefiting you, or if there are any parts, any snags where you feel like this is not working for you. That might be things like, the amount of money is a funny amount of money for me. I wish there was something in between. Or that might be something like, I find it really hard to put in a TESS GI proposal for these reasons. I really want to hear this. I want to hear it all throughout the year, but since we're here in person, I would love to hear it from you in this meeting. You can talk to me directly. You can reach out to the help desk and send us an email to say, these are my thoughts about TESS GI. You can just grab me at coffee. You can shoot me an email. I want to hear your thoughts. In addition to that, you should think about talking with your local TUC member if you do have any feedback about TESS GI or about how the TESS mission is interfacing with the community. There is a page on our website about who is on the TUC so that you can find your local member. They're meeting this week on Thursday. You can grab them, you can chat with them. In that Thursday meeting, there's going to be a discussion where community members, I think, are going to have a chance to speak up, and we're going to be talking about EM3 planning. That'd be a great session to attend. I really encourage you to attend. Finally, in this meeting, we also have the project scientist and the program scientist from NASA headquarters here. So if you have any feedback about TESS and the community, you can feel free to give it to them. TESS cycle 7 begins in September. I'm not going to linger on this. Roland's already showed way prettier plots about what we're going to look at, but you can look forward to some northern, some southern, some ecliptic fields, just all of the TESS greatest hits. Okay, I wanted to talk a little bit about light curve and software that TESS GI and TESS Science Support Center is putting out for the community. First off, light curve is a package that hopefully a few people in this room will be familiar with. Lightcurve is our open source software package for working with data from NASA, TESS, Kepler, and K2. That's why, by the way, I have Kepler and TESS on the screen. 2 minutes, wow. So Lightcurve originally was built for Kepler and K2. Lightcurve was built before TESS even existed. And because it predates TESS, there's a lot of things that Lightcurve doesn't support that are really specific TESS functionality. Lightcurve version 1, which was the first thing that we developed for Kepler and K2, is actually no longer supported. And we're now on Lightcurve version 2, which is this present that we're working in. This is built for Kepler and K2, but has functionality in it to make it work for TESS. It's currently being used by a lot of the community. It's filled with this knowledge and community input from different pull requests and feedback from the community that have gone into Lightcurve. As we move forward, there should be a big question mark against Lightcurve version 3. The TESS Science Support Center is going to be taking Lightcurve and moving it in a direction where it does more and is more able to support TESS, because we would like to move in a future where we can better support all of you. We're going to do this by making Lightcurve more modular, easier to maintain, and still preserving that community input, that community knowledge. Here's an example of something that we've been doing to try and address that. As time has gone on since the Kepler K2 era, there's myriad TESS data. There are tons of high-level science products. There's lots of data at the archive, some of which is community data, community products that you people have put in. And so we have had to make updates to Lightcurve in order to be able to take in that data and be responsive to the fact that there's new data on the archive. So we have broken out the search functions of light curve into its own package. And our plan of attack moving forward is to take the key parts of light curve, break them out, effectively repair some of the modules that are inside of light curve, and then make the package more modular. This should make it so that if you have problems with light curve, it is much easier to find the specific piece that isn't working for you. Light curve search is our first big foray into this breaking light curve down into modular pieces. It's available, it's pip installable. You can install it now as a way to find high-level science products, and it should be more robust than the search within light curve. Moving forward, we're going to be taking these modules and improving light curve to make it more robust, more maintainable. Another example of this is a PRF module. There's a PRF module inside of light curve, which is there so that you can get access to the PRF files. That's pixel response function. What will my target look like on pixels? If I put in an RA index, what will it look like when it's been observed by TESS? We've broken this out into its own module again. And so we're going to be doing this with the key functionality inside of light curve to make this something where, okay, if I only want the PRF, I can go grab that module and make it so that it's easier to find the functionality that you need. We're also building TESS-specific tools. This includes world coordinate system tools. TESS's full-frame images all have world coordinate solutions in them. We've made it a tool so that this is more accessible for you so that you can make the cool plots, like the pretty ones that Roland made, so that you can figure out, okay, if TESS would point here in the future, where will my target land on silicon, and use that kind of astronomy standard that everyone is quite used to, which is the world coordinate system. All these packages are pip installable, and you can come talk to us about it. We're working on a few others. Please come grab us at the help desk session or grab me at any point during the meeting to talk more. I'm gonna skip this one, sorry, Mast. In addition to tools, we're also working on products which will help you detrend the data. This includes products that bake in the motion information from TESS so that you can detrend out some motion noise. Tyler Pritchard is going to be giving that talk, I think on Friday, not Thursday, Friday. So please look out for that talk. I'm going to leave it there. If you have any thoughts and questions, please feel free to contact us. Let us know what you think about the TESS GI call, and we'll be very happy to help you. Thank you.
I think maybe one quick question before our coffee break. Yes, down in front here.
Connie Aerts, Leuven University, Belgium. Hi, Christina. Thanks for this talk. I have a question on the call for GIs, spring 2025. Will we already be able to experiment with 2-second cadence?
I think the question is, will we get 2-second cadence in cycle 8? Is that the question?
As soon as possible. We are very cheap because I don't cost $1.
So I think decisions about that decisions about what EM3 will look like are being made. Come to the session on Thursday, which is the TUC and the community and the mission all talking about EM3 planning, and push for things that you want. And I'm hearing 2-second data.
All right, let's thank Christina again and all of our speakers.
Okay, welcome back, everyone. So we're going to start. My name is Gijs Mulders. I'm on the scientific organizing committee, and I'll be chairing this session. So we're going to start with the Exoplanets I session, and we're going to start with an invited talk by Juliette Becker. And she will talk about TESS and what that means for planet formation. Juliette, take it away.
Yes, the mic is on. Great. All right. Hello, everyone. I'm so happy to kick off this first Exoplanets session after we had such a great introduction to the TESS spacecraft and its functioning. So today what I'm going to talk to you about is how TESS discoveries can advance our understanding of planet formation. And what exactly that means is one of the big goals. Oh, and I should introduce myself. I'm Juliette Becker from the University of Wisconsin-Madison. One of the big goals of a planet formation theorist is to construct a unified theory of planet formation, one that explains all the outcomes. Now, up until fairly recently, the only outcomes that planet formation theorists had to work with was the solar system, which is one pretty limited, apparently relatively rare outcome of planet formation. And even with trying to understand only one outcome of planet formation, Theorists have worked for centuries and centuries and still not quite solved that problem of how the solar system forms. So to find a unified theory of planet formation, we would want to find one that not only explains the solar system, but also explains all the diversity of architectures found in the exoplanet census. And this is something that is actually quite challenging and something that takes not just a single theorist, but the entire exoplanet theory and observation community working together. So to do this, we have to take existing planet formation theories, which are not complete and do currently not explain all the architectures of planets that we've discovered, and we need to update these theories. Now, there's a couple main ways that we want to update these theories. One of them is we want to actually understand the full parameter space that our unified theory of planet formation needs to explain. I mentioned that for hundreds of years, theorists have tried to explain the solar system, and you can construct theories that explain the solar system, but the deluge of exoplanet discoveries over the past decades has made theorists realize that our planet formation theories need to explain a much widened parameter space. So if we really want to understand planet formation, we need to know the full parameter space in which exoplanet architectures can exist. Only by knowing what exactly that parameter space we need to explain is, can we actually start to explain it. After we know that parameter space, the next thing that we want to do is refine this theory using the relative abundances so that we know what outcomes are more or less likely in the exoplanet census. Now, we're going to first talk about this first direction, which is defining the actual parameter space that planet formation theories need to explain. One way to do this, and that has really had a lot of increases in our understanding over the past few decades, is to find unique exoplanet architectures and then find additional systems of those types that allow us to test formation theories. You can't do this, however, by looking at exoplanet systems of only one age. Planet formation is a process that takes place relatively early while systems are young during the protoplanetary disk phase. But then there's significant post-processing that happens after the disk dissipates and the stars evolve. The architectures that we see, even post-star death, as stars start to move off of the main sequence, may continue to change. So what this means is it means we can't look at an exoplanet population of a single age, for example, look at the solar system at 4.5 billion years old and expect that to extrapolate. So to test these planet formation theories, one thing that's really important is to build an understanding of what exoplanet architectures look like at different ages. So here I have a plot of approximate ages for TESS transit discoveries and non-TESS transit discovery stars for which ages have been measured. I'll note a lot of these ages are really uncertain. But what you'll notice is that there is an overabundance of systems at 1 to 10 gigayears in age, with a relative paucity of young systems, which is when the systems are actually forming. If you want to learn more about young planets, there are some great talks today in the afternoon and also in the Tuesday afternoon session. So to learn more about what exactly exoplanet observers and theorists are doing to understand these young systems, check out these talks. You can also check out, here's a small selection of systems that shows what TESS has really been able to do in characterizing young systems. So for young systems, ages are usually estimated by looking at stars that are part of moving groups or clusters where you know the age, and then detecting planets around stars that you confirm to be a part of that cluster. Here's a few good examples to take a look at. But that allows us to do a lot better constraints on the age than looking at only old stars where you can approximately measure the age. Again, most of the planets that we found are around relatively old, gigayear or older stars. So this is a problem. Although we are making some advances in understanding young stars, we generally aren't finding young systems right after they form. We're finding old systems that have undergone potentially billions of years of evolution. So what this means is to understand formation processes, we actually need to look for fossils of the formation process that survive in the properties of the old mature systems. So there's two main types of fossils that we can find. The first of these is planetary physical properties, including mass and radius. As was pointed out this morning, TESS is doing a great job at finding planets for which the radius and mass can both be precisely characterized. These physical properties, such as the density and then eventually atmospheric characterization via James Webb Space Telescope, will allow us to learn some combination of how the planet formed and what processing it's taken between that time and when we're observing it. The second type of fossil we can find is some dynamical history which shows up in the signature of the architecture. So this could look like an orbital architecture of the system or orbital properties of the planets. In particular, we're looking for the orbits and angular momenta that the planets have at current day and how those relate to their inferred initial states. So I'm going to go into depth on the second type of fossil. But first, I just wanted to point out some more that we'll learn about later today in constraining planets' physical properties. So the planet's physical properties include their mass, radius, and composition. This is a plot prepared by the TESS Atmospheric Characterization Working Group, and it shows how you can constrain a planet's composition roughly by looking at its bulk density. And this is something people have been trying to do for a long time. On top of this, atmospheric characterization allows us to learn more about the surface above the planet and its atmosphere. The mass radius measurements that have been made by a large number of groups have allowed us to start to see some physical signatures of planet evolution, including the effects of photoevaporation and core-powered mass loss. Some combination of these processes has started to carve out a radius gap in the exoplanet distribution, where there are kind of a bimodal population of two planetary radii. To learn more about how these masses and radii are measured, you can take a look at Alex Polanski's talk this afternoon. And then there's additionally going to be a lot more on mass constraints later in the session from Madison Brady and Angie Wolfgang. So I'm not going to go into depth about what you can learn from mass radius beyond just, if we want to know where in the disk something formed, we want to know its physical structure as well as its atmospheric composition. So if you can combine current day measurements of those parameters with some inference about what mass loss might have looked like over the history of the system, you can actually start to infer where in the disk these planets formed. Also, there's some great talks this afternoon in the exoplanet section after lunch, and one more talk from Sydney Jenkins on Friday, where you can learn about how once we've characterized the mass and radii of these planets, how can JWST spectra teach us more about their composition and thus their histories. So next up, we're going to move on to the dynamical fossils, which is architectures that planets have retained over billions of years of evolution that tell us something about their formation histories. So this is something that you'll see in their orbits, and you need to really precisely measure orbital parameters in order to understand. So this is going to be a pretty rapid tour because unfortunately I only have 20 minutes, but I'm going to take you through some of the big things we can learn looking at exoplanet orbits that tell us about the dynamical histories of the systems. So the first really useful constraint that you can get is if you can measure period ratios between adjacent planets and also their mass and radius ratios, then you can learn about something about the physics that mediates the processes of planet formation. Period ratios are baked in during formation and also during migration. So whatever period ratios we see today between adjacent planets tell us not only something about how the planets formed, but also how they migrated. In a single system, you maybe can't do very well about detangling these two effects, but with a large population of systems, you can start to understand what pieces of these geometries are primordial and what pieces have come about through planet migration post-formation. Another really useful dynamical fossil is orbital eccentricities. So here is a completely just plain histogram of all the orbital eccentricities reported on the IPAC exoplanet database. I'll note there's a pileup around 0. Some of that's real, and some of that is just because people set the eccentricity to be 0 in their fits. So don't read too much into that. But orbital eccentricity is a measure, again, of both formation processes and post-evolution dynamics. So dynamical interactions in an exoplanet system, such as scattering events, planet-planet interactions, even collisions, can lead to increased eccentricities in the system. Quite often, you will have, if you have an ejection, for example, in a multi-planet system, the planets that are left behind are going to have really high eccentricities. In contrast, really low eccentricities can tell you either that they've never been perturbed into excited states or that some dynamical damping process has decreased their eccentricity over time. So getting really accurate measures of the orbital eccentricities of planets in the TESS sample is important to inferring what's happened dynamically in their systems. If we see a planet with a high eccentricity, then that tells us that there was something at some point, some strong dynamical interaction that excited that. And that's a useful fossil for knowing that this particular system has been active in the past. Next up, another really useful dynamical fossil is stellar obliquities and planetary obliquities. So here's a plot showing both of those. So stellar obliquity is just the tilt between a star's spin axis and its orbiting planet's orbital angular momenta. And then for a planetary obliquity, same idea, but it's between the planet's spin axis and its own orbital angular momenta. The most low energy kind of default state is that these values should be aligned. So obliquities should be low. You should have spins that are aligned with orbital angular momenta, but this doesn't always happen. For example, in our own solar system, we have a good example, Uranus, of a planet that's tilted on its side. Its spin is tilted compared to its orbit. And we think that that was due to an impact at some point in its history that veered the planet off of its original rotational axis. So in exoplanets, stellar obliquities are hard to measure, and planetary obliquities are, at current day, nearly impossible to actually measure. But both of these properties will allow us in the future to refine the angular momentum architectures and systems, and again, infer if there had to be a collision or an impact or something to explain the current day geometries. Finally, I'll take a little more time on these last two. Another really useful dynamical fossil is orbital resonance. So here is a cool animation of the TOI 178 system. So this is a particularly unique system because it has 6 resonant planets. Orbital resonance occurs when you have repeated conjunctions. So you can notice that this animation is showing planets glow in red whenever a conjunction occurs. And these conjunctions will reoccur over time, and this is a very energetically favorable state. So another example of orbital resonance in the solar system is Jupiter's satellites, Io, Ganymede, and Europa. In exoplanet systems, orbital resonance is kind of cool. Maybe you've seen the animations like this one here that create music from the overlapping conjunctions of the planets. But dynamically, it's tremendously useful. A resonant system is an expected outcome of convergent disk migration. So if planets form a disk and then they migrate inwards together, they're expected to be trapped into orbital resonances with adjacent planets. And you get this configuration where conjunctions repeatedly realign. However, the exact geometry of the planets also tells you exactly the style in which the planets migrated. So particular angular configurations of the orbital elements tell you that you might have had, for example, convergent migration. So if we see a planet in resonance, we can expect that this system probably migrated while the disk was still present. And then we can use the orbital elements to constrain those migration factors, including the migration rates and the migration style. Resonant systems are exceedingly useful for this reason. They're one of the strongest constraints you can get about what happened in the disk phase. And because they're so dynamically stable, we can observe systems that are billions of years old and still see a resonance intact. However, one thing that we've learned over the past decades about exoplanet systems is that although a lot of exoplanet systems are close to resonance, most of those systems are not actually in true resonance. True resonance appears to be somewhat rare. So I've put on this slide a few examples of TESS's resonant systems. Some of these are noted as candidates. The reason for that is that to actually characterize something as being in resonance, you need to have really precise measurements of their orbital parameters. So if you only have a limited quantity of data, you can't be sure if something's in resonance or if it's just close to resonance. So the candidate systems are ones where we need more data and more simulations to determine whether they're in resonance or not. You also notice up that I put as here an example, TOI 2525, which is 2 planets, but they're not in resonance. This is just representative of a large number of systems that are close to but not in resonance, which teaches us something new about these architectures. It's currently thought that exoplanet systems that are close to resonance but not exactly in it are systems that were trapped into a resonance and then had some dissipative process after the fact knock them out of resonance. And there's, again, a lot of work theorists are doing to try and understand what's causing this. Is it disk turbulence? Is it dynamical instabilities and collisions in the system? Is it something planetary obliquity related? But we don't yet have the answer. And part of the way we're going to get the answer is get more resonance systems with really strong characterizations, which is what we're starting to get out of TESS. So please continue to find and characterize resonance systems. I also want to point out TOI 1835 and 178, both of which are 6-planet systems in resonance. Now, high multiplicity systems in resonance are really strong constraints on their disk migration process. To check that something is actually in resonance, you have to first determine the dynamical state of the system and confirm that the resonant angles are librating and not circulating. To do this, you have to have very precisely determined orbital parameters. And if you want to learn more on transit timing variations, again, another great talk this afternoon to check out. Finally, if you want to characterize resonance, I mentioned long baselines are best. So ideally, you want to have data over a long period of time so you can measure the orbital elements, including the eccentricity, very precisely. And transit timing variations are great. If you can get those, you have enough data to actually derive variations in the transit times. You can get constraints on the parameters like eccentricity that you can't normally from transit data. So here's an example of the TOI 1835 system. This system was discovered with TESS data, and then a continued characterization of the system by KOPS allowed an improvement of the orbital solution to the point where the authors were able to determine the system was in resonance. So when you find a system you think is resonant in TESS, apply for additional data in future cycles or use other observatories if possible to extend that baseline, and then maybe you will find 6-planet resonant chains as well. All right, back to our rapid tour. We have one more stop today, which is going to be variations between systems of similar architectures. So another really useful dynamical fossil is if you have an architecture that looks to be the same architecture from the same origin, how much stochastic variability is there among system classes? So I'm going to give you my favorite example, which is hot Jupiters with nearby companions. So I'm putting up here a diagram that shows the 3 different formation mechanisms for hot Jupiters. I'm not going to go through them in depth, but the important takeaway from this point is just that there's 3 different mechanisms by which hot Jupiters can form, and theorists aren't really sure which one explains hot Jupiters with nearby planetary companions. So next I'll put up a plot of all of the known hot Jupiters with nearby companions. This is actually still a pretty small number, but it's growing every year. And the 2 systems I've highlighted to start with, WASP-47 and Kepler-730, were both Kepler and K2 discoveries. So this is what we knew about pre-TESS. With those 2 systems, it's really kind of impossible to make dynamical insights on the history of these systems because we only have 2 examples of the architecture. TESS allowed for the discovery of many additional systems. So TOI 1130, 2000, and then also WASP-84 and WASP-132. All were systems where TESS either detected both planets in the system or found the additional nearby planetary companion to a hot Jupiter. As of 3 days ago on arXiv, a brand new system, TOI 1408, was posted. And this system actually, I wanted to point out because it made me question what I know about hot Jupiter systems with companions. Up until this system, none of the other systems have been in orbital resonance. And up until I saw this paper very recently, like yesterday, I thought that that was an inherent part of the hot Jupiter with nearby companions migration process. It did not maintain resonance. However, this TOI 1408 is a counterexample to that and demonstrates that these systems are sometimes in resonance. So this example of architecture shows how valuable individual TESS discoveries can be. They can take a population where we kind of think we know what's going on, and they can cause us to take a step back and say, maybe we don't actually understand the full variability of this class of systems. If you want to hear more about hot Jupiters, then check out Joy Rodriguez's talk this afternoon and Noah Vowell's talk on Friday. With that, I am a little over time, so I'll just put up my conclusions and explain my final takeaway. Theorists can make up whatever we want. We can come up with any planet formation theory that explains anything. But the only way to actually know that your planet formation theory is correct is to test it with data. So to get this unified theory of planet formation, we can't do it with theory alone. We need to use the observational census of planets as the most valuable input to the model that both tells us what architectures our theory must explain, but also constrains us and ensures that we don't come up with theories that are maybe potentially reasonable, but don't explain the observed census. So my request to all of you TESS observers is please continue to expand the census and get that follow-up data so we can know if these systems are in resonance. That's super useful for us theorists. All right, with that, I'll take questions and thank you all so much.
Thanks, Juliette, for that great talk. We're now taking questions. We have time for a few short questions. Just a reminder, can you state your name and affiliation before the talk? So we have one question there in the middle. And then we'll do after that one question there as well.
Hi, Johanna Teske from Carnegie. Thanks for this wonderful talk. So as an observer, me speaking to you, what do you need in terms of the precision for eccentricity and obliquity measurements? Like how, if I get 0 plus or minus 0.1 for eccentricity, is that really 0 or do you need to know better than that?
Yeah, so for eccentricity specifically, it would be better to have errors on order of like 0.01%, but I will take whatever I can get. Like so many observational fits fit eccentricity equal to 0, which is usually right. But getting an actual like refined distribution of eccentricities between 0 and 0.1 would be tremendously useful.
Thank you. So we had one question there and then we can go over there.
Hi, Elisabeth Newton, Dartmouth College. So you showed those 2 6-planet systems that are both in resonance. Do we have enough data to explore whether high multiplicity systems are more likely to be in resonant chains? Or is that just a bias of our choice to observe those 2 systems in detail because they had 6 planets and they were cool?
Right, yeah, so good question. So the question is, we had a couple of 6-planet systems. Do we have enough data on others to say that they're not in resonance like that? So we have a few examples from Kepler of high multiplicity resonance systems. I do think one of the limitations we have in TESS is that most of the systems don't have that high of multiplicity, in which case, by definition, we couldn't have detected the resonance. There are examples of systems where we found, say, a 4-planet resonant chain, and then an additional planet was found afterwards to be a part of that chain. So I think the probably easiest path to 6-planet plus resonant chains among the systems we've already found is expansion of chains that we think are shorter, but actually just have planets we haven't found.
Okay, let's take the final question there.
Manny Rivas from Stanford. Is our solar system a resonance system and is it required for life formation?
Great question. So we looked at our planetary system as an observer. We would not characterize it as a resonant system. However, there is resonance in the solar system, not between the inner planets in the terrestrial planet zone, but in the Kuiper belt. So for example, Pluto is in a 3:2 resonance with Neptune, and there's an entire population of objects in the outer solar system that are in resonance. We can actually use the existence of those resonant planets or objects in the solar system to constrain the migration rate of Neptune, which is really useful. So although we don't have planets, we can still learn a lot from resonance in our own solar system.
Thank you.
Okay, let me quickly see if our speakers ready. Yes, so with that, let's thank Juliette again for this great talk.
All right, hello everyone. I hope you all had a good lunch. Please go ahead and find your seat. I'll give you guys 20 more seconds to find a seat, then we'll get going with this second exoplanet session of the day. All right, thanks so much. So we're going to start off our second exoplanet session of the day with a talk by Mike Lund from Caltech and IPAC NextSci. And he's going to tell us about ExoFOP, evolving support for TESS and future missions.
Hi, yeah, so I am here on behalf of the ExoFOP team, which this time around has, I think, higher turnout than we normally do, since both Jesse and David are also here. And so this is sort of our standard update of what we are up to and how it's helping TESS. So the Exoplanet Archive with ExoFOP is funded to support the community follow-up for first for Kepler and K2 and now for TESS targets. Sorry, I am shorter than the podium for this angle. I'm using it for support, so I'm gonna turn this slightly. There we go. And so this is a constantly evolving site to try to match the needs of the community. So I'm going to do a little bit of how it's been used over the last year or so, and what's the new features are, and sort of what we have on the horizon after that. There we go. So this is a look at where our numbers were in June of 2023 in terms of the number of files, the number of parameters, the number of observations that have all been submitted. One thing I'll note with that is that these numbers also reflect that not only are these the numbers from ExoFOP TESS, but we've also, prior to the last year, migrated over all the data from ExoFOP Kepler and K2. So we've been working to get this to now be a site that has all the follow-up for exoplanets in one spot. So the numbers, how they have changed since then, last year, we've seen thousands of new observations for the RVs, for the direct imaging, and for the time series observations. We're averaging something like 160 or 170 new files a day over the last year. So there's a whole lot of data coming through here. And as a result of that, there's now over 260 papers that currently include ExoFOP in their acknowledgements. That's over 100 in the last year. So we are pleased to see that ExoFOP is taking a role in helping a lot of this research going on. And again, if you are using us, please include that so that we can include that in these numbers. There we go. So I'm going to start off with some of the new features that have shown up on ExoFOP over the last year that you may or may not have noticed happened. So first of all is we've added the Gaia DR2 IDs to the Find Tick IDs service that we have. So from the ExoFOP homepage, if you find the stars box on that page, the first link on there, up there is Find Tick IDs. And so you can use this either with our API that we have, and you can get a JSON format back that will include the DR2s. You can do this for a single object. You can do it for a list. You can also just do an individual little web query there. And again, you can get those Gaia DR2s. And so for this, we're using cross-referencing tables that we have behind the scenes to sort of help get those DR2 IDs. We've also added the Habitable World Observatory's target list, which was generated by the NASA Exoplanet Exploration Program. Actually, I'm going to go back for a moment if I can. In that same star box down at the bottom, you can find the link to this. And so that's the Habitable World Observatory target list. And then one of our more involved interface additions is for the large tables that we have. So the TOIs, the CTOIs, all three of the observations tables, that habitable world observatories list and the stellar companions table. We've also now added the ability for you to, when you're logged in, to adjust the order of those columns, adjust which columns you're seeing, and then save that as a new default view. So you can customize these tables now. And you can have multiple views if that's helpful. So that you can really customize these so that this will more smoothly fit in with your workflow. And so you can also go through and manage this and sort of select what do you want your default view to be. So you can set up multiple views, you can swap back to the default one, you can delete old interface views that you no longer need. And then we have a couple things that are in the realm of coming soon. One of these, sort of based off that habitable world, the HWO list, is that we are working on having the ability to create your own custom target lists. So all of this is, everything on this slide is a idea of where this will end up, but I'm not saying anything is fully confirmed other than we'll get some sort of function like this on there. With the idea that this will likely have the ability to either have lists of stars or lists of exoplanets, and to allow teams to create their own personalized lists, for missions to have specialized lists. So this is to make it a lot easier to get to the subsets of targets that you would like to see in a single view, rather than having to constantly try to filter things down yourself. So we are working on getting this set up. Look for this hopefully somewhere soon. And then the other thing that we're working on, and this is part of that goal to be a location for all exoplanet follow-up work, is that we're also developing how to add new planet candidates to this. So currently, the support really just is for TOIs and CTOIs. And so both of those are very explicitly TESS-oriented. So we are working on how to expand this so that you can basically put in candidates for any planet search that's ongoing, which is a tricky thing that we're making sure that we do right. So it's a slow process that we're looking forward to getting out there so that you can submit this and link candidates to any project that you're working on. So the exact particulars of what this will look like will be coming, but this kind of gives a rough idea that we can have sort of additional planet candidates, that this will keep track of whether or not they're TOIs. The underlying thing that this is still using is this is all still presuming that everything does at least have a tick ID. And I think that will remain a key part of this, but that no, it won't be presuming that you're suggesting a candidate because it is a tick planet. So this is going to allow us to go beyond just all the number of planets that are coming in, or the number of planet candidates coming in from TESS, and sort of have this all in one location. And so that is also something that we have been working on since last year. And so we are also looking forward to rolling that out soon. So those are our two main things that hopefully by next year we'll have much more concrete releases on them. And of course, if there's feedback that you have on any of those in development features, this week is a great time to find us and provide us that feedback as we're still trying to sort this out. I think that covers everything that we are up to right now. And we look forward to seeing how much more this grows the next time we all get together. And the ExoFOP has continued to grow with all the work that's being done.
All right, thank you so much to our speaker. We have time for a few questions. All right, so do you have a question or are you running the mic? Okay, great. So while you guys think of your question, I actually do have a question because earlier this morning we heard that ExoFOP is a good place for observers to deposit observations that they've made. Do you have suggestions on what observations might qualify to be worthy of being included on ExoFOP, or how might one do that?
So I'd say, I think any observations that you're taking, I think we can accept. I would recommend that it's better, for example, if you were doing something like time series observations, to provide something like the final light curves rather than every image you took over the course of the night. So I think probably some of the summary data of those observations is probably a little bit closer. Because if we had everything everybody had, I don't think we're fully funded for that much data, but definitely for the summary data, I think that's very helpful. We've very deliberately not constrained what you submit, so that if someone has something that they feel is scientifically useful, we're not going to reject it because it didn't fit, the right kind of a format or something. So if people have it and they think it's useful, submit it.
Okay, great. Maybe if they even don't know if it is useful for someone, maybe it will be useful eventually down the line. Any additional questions before we move on to the next speaker? All right, let's give our speaker one more round of applause. Our next speaker will be Pierre-Alexis Roy from the University of Montreal, and he will be the first in this session to start telling us about what JWST can teach us about exoplanets discovered by TESS. Take it away.
Yeah, so hi everyone, I'm Pierre-Alexis. I'm a PhD student working at University of Montreal with Bjorn Benneke. And yeah, I'm very happy to be here today and to showcase the work that we've done looking at TESS sub-Neptunes with James Webb. Now, I want to start with the mass radius diagram of small planets, which we all know by now, with the smaller planets that are consistent with being rocky in composition. These are the exo-Earths, the super-Earths. But for the sub-Neptunes, we don't know quite yet what their composition is, because there's an inherent degeneracy with their metallicity. You could have a sub-Neptune with a hydrogen and helium dominated upper atmosphere with either a large rocky core underneath, that would be a gas dwarf scenario, or a large mantle of ices, a mini Neptune scenario. But you could also have a water world where the dominant species of the atmosphere is a much heavier molecule like water. And it's important to understand the composition of sub-Neptunes, because that's what's in the end going to help us understand their origin and their formation. Because if a planet forms close to the host star at the interior of the ice line, then you expect it would form with a hydrogen and helium primordial atmosphere, which would be low in metallicity. But if it forms further away from the star, then you expect water and other molecules to be available in the solid phase and be accreted to form a bulk fraction of the mass of the planet, which would lead to higher metallicity atmospheres and envelopes, either the mini Neptune or the water world scenario. So the way that we can break this degeneracy in these compositions is through measurement of the mean molecular weight. Because as I said, if you have a hydrogen and helium dominated upper atmosphere, you're going to measure a really puffy atmosphere. You're going to measure a low mean molecular weight, same as that of Jupiter. But if you measure an envelope that's dominated by water or other molecules, then you're going to measure much higher mean molecular weights. And the way that we can distinguish and measure this mean molecular weight is if we're able to obtain a precise transmission spectrum of a planet and measure multiple bands of the same absorbing species. So that's the next step. We need to use James Webb to obtain precise transmission spectra and try to measure the mean molecular weight. And one of the best targets to do just that is TOI 270d. So this is a planet that's 2.2 Earth radii, so just above the radius valley. And it's rather cool. It's at 350 Kelvin, but most importantly, it has a really, really high TSM. It's one of the most favorable targets to observe in terms of transmission spectroscopy. And we observed it twice with James Webb, once with nearest SOS, and once with Vanderspek G395 in order to obtain a full spectrum from 0.6 to 5.3 microns. The light curves are very well behaved, very precise light curves. And if you're wondering what's happening with the G395 visits, well, planet B, the inner super Earth of the system, decided to photobomb that transit. So we obtained free data, which is always cool. But if we look at the transmission spectrum that we obtained from these light curves, it looks something like this. So this is a very rich transmission spectrum. There are no clouds that are hiding the molecular information from the upper atmosphere. We detect methane, we detect water, we detect CO2. We even detect tentatively sulfur species like SO2 and CS2. But perhaps most importantly, we detect 5 individual bands of methane absorption, which, as I said earlier, is going to allow us to measure the mean molecular weight of the atmosphere of this planet. And so what's that going to be like? Are we going to measure something that's 2.3 MUs, like a hydrogen and helium dominated atmosphere, or something that's much, much higher than that? And when we do our retrieval, we measure the mean molecular weight, we get 5.5 plus or minus 1. So basically, none of the scenarios that we were thinking of beforehand can explain this planet. So what's going on? We can look at this mean molecular weight in terms of the atmospheric metal mass fraction. So basically, we're asking the question now, for the total atmospheric mass, what fraction is in the hydrogen and the helium, and what fraction of the mass is in those heavier volatiles like water, methane, and CO2. And we find that 40% of the atmospheric mass is hydrogen and helium, and 60% of the atmospheric mass is into those volatile metals. And that's something very important for our understanding of the composition of sub-Neptunes, because it means that those metals, they are up there mixed with the hydrogen. They're not under it somehow layered in composition between this hydrogen and helium atmosphere. And this is expected because for the temperature and pressure conditions on sub-Neptunes, water is expected to be at the supercritical phase, in which case it is miscible with the hydrogen, and it can mix without ever separating. And this is the vodka planet, as my supervisor Bjorn is calling it right now, because miscible is like water and alcohol. If you mix them, they're not going to separate, as opposed to, for example, water and oil. And so this forces us to look at the composition of sub-Neptune a bit differently. So we would expect that most sub-Neptunes that are warm or warmer than TOH 70D would have this kind of envelope in which the metals and the hydrogen are well mixed into a miscible envelope. And then only when you move to those lower temperature planets, you could start to have water condensing out to create that upper layer of hydrogen and helium. And it could potentially condense out into a liquid water ocean. But perhaps even K218b is not even cold enough for those scenarios. More observations will come on that planet. But now that we have this idea that the atmosphere is mixed, then we have the mass, we have the radius, and we have the mean molecular weight of the envelope, which should allow us to obtain the full picture of what's the composition of that planet. And we do that with interior structure models that were produced by Daniel Thorngren. And what we find is that 90% of the mass of this planet is found into the rocky core, and that 10% is found into the envelope, which, as I said earlier, we measured to be 40% biomass hydrogen and helium, and the rest would be those volatile metals. So how can we interpret this in terms of the origin and the formation of that planetary system? Well, it would mean that that planet formed inside of the ice line. It first accreted an envelope of hydrogen, a primordial atmosphere, and then the interaction between that hydrogen and the interior, a magma ocean, would have created large amounts of water of a carbon-bearing species that we are now observing in large amounts in the atmosphere today. And This goes along with theoretical work that was done by Hilke Schlichting and many others that show that hydrogen is not inert on top of magma. It's going to interact and outgas some new molecules. So this is TOI 270d. But of course, we only have 2 planets in that temperature and size range observed with James Webb so far, TOI 270d and K218b. So we really want to probe more of those planets. And one that we have recently looked at is LP 79118c, which in terms of temperature is right in between K218b and TOI 270d. So we observed that planet with near-spec prism to obtain the same wavelength range from 0.8 to 5 in one observation. This is a very similar planet to K218b, but the TSM is very, very high. It's even higher than TOI 270d. So the transit depth is 1.5%, and the star is super bright in our sky. It's as bright as WASP 39. So basically, these are hot Jupiter quality light curves for a sub-Neptune. And if we look at the spectrum that we obtain, then it's a bit different than what we saw for TOI 270d. So what's going on? We see the methane. We see hazes that are hiding the upper atmosphere at short wavelength and that have a fading opacity toward longer wavelengths. And most importantly, we don't see oxygen-bearing species. We don't see the CO2 that we were seeing in TOI 270d and K218b. And that would be first observational evidence of a diversity in the composition of sub-Neptunes, which was expected, but that we're observing now for the first time. So to conclude, James Webb revealed one of the most precise transmission spectrum for a sub-Neptune or a temperate sub-Neptune in TOI 270d. This forced us to reconsider our understanding of the envelope of sub-Neptunes and to find out that their atmosphere are probably mixed and miscible rather than being stratified. And LP79118c points to an intrinsic diversity in sub-Neptune composition. And I want to finish by saying that I think these 2 planets are super great examples of the success of the TESS mission, pointing out the best favorable targets to observe with James Webb, and James Webb delivering those very nice scientific results. Thank you.
All right, thank you so much for that excellent talk. We have some time for questions. All right, I see one up here first.
Great work. I have one question, then one comment. The question is, I wonder if the people working on the magma ocean scenario have any definitive evidence of some species that would help clinch that picture. But while you're thinking about that question, just a comment to George and let's just say the powers that be, we definitely want those, I think you said 54-day observations or the much, much longer periods that we're hopefully going to talk about Wednesday afternoon, because we want those much cooler planets so we can get the water worlds later.
Yeah, on the volcanism plus magma interaction side, yeah, I'm not the expert on that part, but I think usually you'd expect sulfur and carbon species to be generated by that. Of course, now it's more complicated because you have a huge envelope on top, but yeah, I'd be curious to look at that more. Thanks.
All right, next question.
Hi, thank you. Very interesting talk. Remind me, maybe I'm wrong here, but supercriticality happens at high pressures. And transmission spectroscopy is what we observe when we look at the pressures of about one millibar. So it's not the same area.
No, but I think we're observing at 1 millibar, but under that gas phase, there's going to be supercritical phase. There's not going to be a phase where it's going to condense out without going through supercritical phase. Yeah. And then everything would be miscible.
So it's well mixed.
Yeah, well mixed. Exactly.
Hi, yeah, this is great. I was wondering if, especially for the third planet you spoke to, if there are formation implications for the absence of carbon dioxide in the upper atmosphere?
Yeah, this is what we're kind of finishing up before submitting this paper. There's also a lot more photochemistry around this planet. This is probably the reason why we see so much hazes and clouds. The star is a more active star. It's a very late M dwarf. That's why the signal is so good, but I think there's a lot of things in the photochemistry side that can explain those differences, and that's what we're investigating right now. Yeah.
All right, thank you so much. Anyone else who has additional questions we didn't have time to get to, please post them on the Slack. All right, let's give our speaker one more round of applause. Our next speaker will be Ben Rackham from here at MIT, and he's going to continue the JWST conversation and add in some Hubble Space Telescope as well, and tell us a little bit more about transmission spectra from TESS planets. So take it away, Ben.
Thank you. Yeah, I'm a research scientist here at MIT, and it's great to be able to talk to you all. I'm going to be talking about how we can use HST and JWST spectra alongside TESS photometry to try to constrain stellar photospheres and unlock the transmission spectra of the coolest, smallest exoplanets. And I forgot to grab the doodad. Is this it? Yeah, big arrow button. Big arrow button. Thank you. Okay, so with the time that I have, I'm gonna give you a little context about why we care about stellar activity in the context of transits. I'll introduce these two new legacy archival programs in which we're trying to address this question. And then I'll give you a look at our first results combining HST spectra and TESS photometry to try to understand the photosphere of this really famous hot Jupiter host, HD 189. So a little bit of context. Why do we care about stellar activity? Well, we're all jazzed about transiting exoplanets because we can learn so much about them. We can measure their sizes from the transit depth. We do this over multiple wavelengths to build up an understanding of how the planet's apparent size varies with wavelength. And that tells us about absorption or opacity sources in the planet's atmosphere due to molecules. JWST is great for this, as we've just seen in the last talk. And JWST is performing so well that in principle, we could use that facility with enough transits to look for biosignatures. This is pointed out in a recent paper by Vicky Meadows. In the TRAPPIST-1 system, we could detect signatures of chemical disequilibria with JWST. The number one hurdle we have, though, to do that is the fact that the stars contribute signals into transmission spectra as well. The photospheric heterogeneity or spottedness of an exoplanet host star impacts transit depths. And it does so through an effect we call the transit light source effect. Boils down to the fact that transits are differential measurements, but we don't know the reference spectrum as well as we'd like. So what we do is, naturally we assume that the spectrum illuminating the planet's atmosphere is the full disk spectrum we get before and after the transit. We normalize transits to that spectrum. But the actual light source that's illuminating a planet's atmosphere comes from a spatially resolved region on the stellar disk that we can't directly probe. So any difference between the full disk spectrum of a star and that transit chord spectrum ends up imprinted on the transit depth measurements. And that signal from the star can sometimes mimic or mask those from planetary atmospheres. At the end of the day, we're getting two signals. One wavelength-dependent signal from the photospheric heterogeneity of the star, and another wavelength-dependent signal from the exoplanet's atmosphere. And we've seen with some JWST observations already that this is the bottleneck. So this is that same TRAPPIST-1 system that we would like to search for biosignatures potentially. And the easiest planet to access is TRAPPIST-1b. But in back-to-back observations led by Olivia Lim, we see two totally different spectra for TRAPPIST-1b. We have different spectral slopes of the planetary of the transmission spectrum, and we have an offset of 400 parts per million. That's kind of hard when you're looking for a 10 ppm signal. So this is telling us that this is the bottleneck. And the road to terrestrial exoplanet atmosphere characterization is going to run through their stars. This was pointed out recently in this nature perspective from the TRAPPIST-1 JWST community initiative. I won't go through all of it, but essentially what I wanted to impress on you is that when we find a new transiting exoplanet, a terrestrial one, we can do eclipse spectroscopy, like this recently announced 500-hour DDT program on JWST. And if we see there's no atmosphere, then we're done with that planet. But if we see that there's evidence for an atmosphere and we really want to constrain it, the road to constraining the atmosphere goes through understanding the stars better. In other words, the best studied exoplanets must have the best studied host stars. So that's where these two legacy archival programs come in that we've recently launched on HST and JWST archives. Essentially, what we're interested in is using that out-of-transit stellar spectra we get from these facilities, which are some of the most precise, absolutely calibrated stellar spectra of these stars, to understand the stars as well as we can. Typically in an exoplanet observation, you just normalize to that data and you never look at it again. But we know now that if the stars aren't perfectly well behaved, that doesn't work very well because like what I just explained, the transit light source effect, but also there's signal in that data that we're not harnessing by just normalizing the transit depths. And so we can probe what's going on in the star by looking at that out-of-transit stellar spectra. In these programs, we want to know what can we learn by just focusing on this data that we get during the observations naturally. And so we're going to do this with 50 visits of HST in the archive that cover 16 exoplanet host stars with the STIS, CCD, and with WFC3, both the UVIS and the IR modes. And we're also going to do this with 21 host stars, 37 visits, using JWST data from NIRSPEC Prism and NIRA-SOS. Our goals for these programs are very similar. We want to know what is the photospheric heterogeneity of these host stars, how spotted are they, how does that vary with time, and we want to derive for the community as a legacy product transmission spectra of the exoplanets that account for that contamination. We're also going to use TESS data as available to try to constrain the distribution of the active regions on the stars, which I'll get to in a moment. So with the time that I have left, I just want to tell you about our first results on the famous star HD 189 using HST and TESS data. And so you probably know this famous hot Jupiter. It's one of our most easily accessible hot Jupiters, but maybe you know, maybe you don't know that its host star is a very active K-dwarf, one of the most active exoplanet hosts. And so that actually leads to two competing explanations of the transmission spectrum for HD 189b. We see this very strong scattering, or very strong slope in the optical that has been interpreted as scattering by planetary haze. And that's why you see this blue exoplanet. But as pointed out recently after those initial results, that this could also be due to the impact of unocculted star spots, creating what looks like a scattering slope, but actually we're just seeing the impact of unocculted star spots. So we wanted to look at the HST data from these observations themselves, look at the stars, see if we can answer this question of what competing explanation is more viable. And so in work led by MIT graduate student Isaac Narrett, who's presenting a poster here, 1.33, about this project. We looked at the WFC3 data from 3 visits spanning over a decade. And what we did was we tried to fit that HST spectrum, very precise HST spectrum, with models that had 1, 2, or 3 stellar spectral components. We find that the single component models do not fit the data. The 2 component models do a good job of fitting the data for all 3 visits, and 3 component models don't really add anything to the picture. So we conclude that the HST spectra are best fit by the 2 component models, and we have reason to think that this is actually physical, which I'm going to get to right now. So we interpret this 2 component fit as the physical imprint of a photosphere and a large spot filling factor on HD 189. Why do we do that? Well, first of all, the parameters that we infer are persistent from visit to visit. Within a single visit, the temperatures are consistent and the filling factors are consistent. And between visits, the filling factors vary for that second component, but the temperatures of the 2 components that we retrieve are always consistent. This result is also robust to what choice of stellar models we use. When we take out the Phoenix models, plug in the newer MPS Atlas models, we get the same result. We see about 30 to 40% spot coverage, depending on the visit, and the spot temperatures are consistent. So the conclusion from this work is that there's actually more than enough spots to explain this spectral slope using unocculted spots on the photosphere of this active host star. We wanted to go a little bit further and ask, if we can constrain the distribution of these spots on the photosphere of HD 189 using TESS photometry. And there are two sectors of TESS photometry available for HD 189. We see evolving, we see rotational modulation that changes with time, but at its peak is about 1.5%. And that's something that we've seen from other facilities as well. And so, you know, fitting a spot model to a single band of photometry is it's a very highly degenerate problem. So what we did is we took a probabilistic approach and we asked what families of spot parameters are consistent with this kind of variability that we see. And so using a cool tool called Spotter from Leonel Garcia, we find that most of the spot coverage must be distributed axisymmetrically about the star. So in other words, to reconcile HST spectra and TESS photometry, most of the variability, most of the spot coverage is not actually contributing to variability, but it's spread across the star in a way that it shows up in the spectrum, but not in photometry. If the spot emergence on HD 189, a K-dwarf, is like what we see on the sun with active latitudes, then we hypothesize that most of those active bands are actually so spotted that they're no longer contributing to the variability. They're just like bands of spots like you would see on a brown dwarf. Another possibility that's been pointed out from Doppler imaging studies is you could have a large polar spot. That's going to affect your transmission spectrum, but it won't affect the rotational variability. So these are two families of possibilities that might reconcile both the HST and TESS data. And if you want to know more about cool open source tools that Leonel's developing, you have to wait no longer than tomorrow, where he's going to give a talk about another cool tool he's made. So the things to take away from this talk is that we are using HST and JWST stellar spectra alongside TESS photometry to constrain more than 30 exoplanet host stars with the goal of understanding the stars so that we can reduce biases in transmission spectra. Our first study on HD 189 has shown that this K-dwarf has a persistent level of spottedness that can more than account for the spectral slope we see in the transmission spectrum of HD 189b. And adding in the TESS variability into this analysis, we find that most of that spot coverage must be distributed axisymmetrically. And we suggest that either filled latitudinal bands or polar spots could account for that finding. And this is just the first of more work on more than 30 host stars, 100 data sets, where we're going to be trying to do the same sort of analysis and provide transmission spectra to the community that account for the stars. So thanks for your attention. I can answer your questions.
All right, thank you so much for that great talk. We have time for a few questions. So I guess, oh, we have one right there in the middle. Oh, sorry, didn't see you. Go ahead.
Sure.
Yeah, go ahead.
All right. This is David Ciardi. Next slide. Ben, this is a nice talk. Can you talk a little bit about differential rotation and its effects on the modeling?
Sorry, can you
talk a little bit about differential rotation?
Differential rotation.
And its effects on the modeling and the interpretations.
Yes, yeah. So differential rotation, I think that's going to mainly be an issue when you're trying to determine rotation periods because you have spots that are rotating at different speeds. What really matters for understanding transmission spectra is what did the star look like at the time of transit? And so that's our motivation actually for focusing on these data sets themselves, because we don't need to get any contemporaneous observations. We don't need to get observations that extrapolate in time, but we can look at the time of transit, what did the star look like and how would that in fact impact the transmission spectrum?
About the two different axisymmetric spot coverage models, can you make any statements about those two from the occultation and whether you get any spot crossings in the transit cord?
Yeah, so HD 189 definitely has spot crossings. That's been shown with previous HST data sets. And actually, if you look at the TESS photometry, you can see the spot crossings there, which is cool. So if you had keen eyes, you would notice in both of these models, the filled latitudinal bands, where the modulation is due to overdensities and underdensities of the spots, the active latitudes roughly with the transit cord. And so where there's this overdensity of spots, you would get a spot in the transit cord. Where there are fewer spots, you might not see them in the transit cord. And in the polar model, right, we have to have some spots at the mid-latitudes. So in that polar model, most of the spots occur at the poles, but there are still some active latitude spots that come and go.
All right, we have time for one more question. I see one up in the back.
I wondered, with these observations of HD 189, did you account for the night side emission of the planet contaminating those out of transit data?
We did not. That could be a concern for HD 189. Can't quite remember off the top of my head what the night side emission might be, but with the level of heterogeneity that we're seeing on the host star, the contributions from both the quiescent photosphere and the spots, I think, are a few orders of magnitude more than the emission that we're going to see from the night side of the planet. So I think it's okay to safely ignore that in that case, but maybe not in every case.
All right, thank you so much. I know there's a lot more questions, so please take them to the Slack. And one more round of applause for our speaker.
Thank you.
All right, our final speaker of this session is going to be David Armstrong from the University of Warwick, and he's going to be telling us about the NOMADS program.
Thanks, and thanks for the chance to talk about this observation program. So this is a large program on the HARPS spectrograph we've been running for several years, focused on planets in and around the Neptunian desert. Now, here we go. Now, as with any program, any large observation program like this is the work of a lot more people than me, only some of which I've probably managed to fit on the bottom of the slide. Particularly in terms of this talk, these three, Lauren Doyle, Aries Osborne, and Lorena Acuna, one of whom's in the audience, and Lauren has a talk on Wednesday at the Brown Dwarf session. I encourage you to attend. Now, what is this desert and why should we care about it? Now, the Neptunian desert's been known about for a very long time. There's a region of Neptune size and mass planets quite close to the host stars, where we've seen a big gap at day out of these planets. And canonically, that's been because tidal disruption has sort of destroyed and removed the planets at the top of the desert, and photoevaporation has evaporated and shrunk the ones lower down and removed them from it. Now, this was a very clean picture for a very long time. One of the, and this is my very biased opinion here, big results from the TESS mission is finding a selection of planets in this desert and showing that it is in fact populated. Now, you'll see on this plot that there's also something called a ridge off to the side, and this is a very preliminary result from Amadeo Castro Gonzalez, which is a paper under review. I have got his permission to advertise this, by the way, which shows that there's some evidence for a pileup of Neptunes at 3 to 5 days orbital period just outside this desert. And an interesting, well, it lines up with the hot Jupiter pileup, and it's an interesting edge to what was previously a semi-undefined region. Now, what has TESS shown? If we take this region sort of quite close in inside there, and I plot the planets, the confirmed planets with masses on, these are the ones there. So there's 16 planets now inside this quite conservative set of boundaries, and they're closer in than previously accepted desert boundaries as well, demonstrating that this is really starting to be quite a populated region. Now, what do these planets show? If we put them on a mass radius diagram, they're all pretty dense for where they are, and they start raising some quite interesting questions. How do they get to lie in this desert in the first place? Why do these processes not work in the way that we thought they were going to work, and that theory had shown pretty consistently that they were working for a while? Why and how do these planets manage to stay? And because several of them are particularly odd, they have very high masses, 30 Earth masses, 50 Earth masses, 70 Earth masses in one case, despite being about the size of Neptune. How did they manage to get this amount of mass, and how did they remove the big volatile envelope that you would expect? These are well over the threshold for runaway gas accretion that we think Jupiter would have formed by, 10 to 20 Earth masses. They should have a large volatile envelope, and they don't. It's a bit of an open question. Now, there are several bits of evidence building their way up to this. I've tried to condense a few of them onto this slide just for ease. Photoevaporation, as we expected, can work, but it depends a lot on the details. If something starts off at a Jupiter mass and it arrives a bit late, it won't photoevaporate. If it arrives very early, before and around disk dispersal, it can be possible, but it depends a lot on the specifics. So how early these planets get to this location is quite an important bit of evidence to find. Getting to these high heavy element masses is particularly challenging. You can get there in a few different ways. Most of the ways I've seen involve invoking collisions between forming planets to build up the mass. Or you can sometimes get a planet very close to the star very early where there's a high heavy element mass concentration. There's some evidence in the host star metallicities. A few people have started spotting that these planets very close in the desert have higher than average host star metallicity, similar to the hot Jupiters. But that's always been done with very low numbers up to now. And finally, just to confuse the picture, you still get these very dense Neptune-sized planets outside the desert as well. Neptune-size, higher mass. TOI815c, there's some others. And so it's not necessarily a question of just being in the desert. There might be conflicting processes going on here. But one way or another, we have a pile of very odd planets, very high masses, and yet not particularly large, populating a region that was previously thought to be empty. So we started trying to see, well, what can we do? And what can TESS let us do to explain these problems? Now, even about 3 years ago when we started this off, there were a number of TESS TOIs in the desert, 272 on this plot, using some somewhat broader desert boundaries. And we thought that would be a great population to try and target. Now, thank you to Johanna for pointing out the biases in doing RV surveys, because we thought up to this point, we'd been doing some pretty observation of opportunity style programs. You pick the bright targets, you pick them as they come out, you try and find the interesting ones, and it leads to lots of biases. So we thought we'd try and do this one a bit differently. We had quite a few nights. We thought we'd define a merit function and see if we could actually make the proposal go complete down to a certain line in this merit function. So we had a proper observation strategy and then completed it. Now, given the time, we estimated that we could cover about 30 systems this way. And if you account for other programs that were also observing targets, which we weren't going to duplicate, you can build that up to more like 50 or so to get a nice sample of planets. So what kind of merit function did we use? Something very simple. It prioritizes bright targets and it prioritizes targets deeper into the desert. So we applied this along with a series of vetoes based on false positives and very fast rotators and defined a target sample that way. Now, what actual value things have in terms of this merit function isn't very important, but what's important is that we try and complete it down to a certain limit. This number is 5, it's basically arbitrary. But the result was 70 TOI candidates that we aimed to make sure each one had observations down to a certain level of precision. Some of them had been published already, shown on the plot. Some of them had not. The yellow circles are ones that we went for. And then some of them were known to be flat lines from a program we were running at the same time. And to skip over years of work in a single slide transition, I do mean years, of those 70, 20 of them were null results, we got flat lines. 50 of them are now confirmed planets, some of them from other programs, some of them from ours, but all of them done in this sample. And this is them shown on the Gaia Hertzsprung-Russell diagram there. Now, it's quite interesting to me, and we didn't necessarily expect this, that basically all of the null results are up at the high mass end of the Hertzsprung-Russell diagram, which is quite an interesting factor for anyone choosing targets and running vetting programs. Why that is, there's a higher binary fraction up there, which is a big clue. But if you're looking for false positives, that's the place to go. But you'll notice there are confirmed planets in that region as well, so it's not as trivial as just cutting them out. Now, if I show them on a mass radius diagram, you can see a whole selection here, and they're all dense for their region, which is what you kind of expect for things very close in. And the null results are shown as arrows. So pretty much all of our flat lines are in regions where you wouldn't necessarily expect planets as well. So they were hit to a level for us to be able to show that. Now, what can we do with that sample? And the rest of the talk, I want to talk about what we can get out of it. Because we now have a sample of 50 planets chosen in a somewhat principled manner, and they're all close into the desert, and we have these questions, and what can we try and answer? So for the rest of the talk, I'm going to focus on this gold sample of things that are actually closer to Neptune in size. I say closer, it's 2 to 10 Earth radius. There's a bit of a broad thing there, but I don't want to confuse the hot Earths that were on the edge of this previous desert boundary into the picture. And that takes us down to 34 planets. Some interesting points to note just on this plot, though. You can see the null results on it. Most of them are in this deep desert region on the far left in the middle. Don't know if that means there's a higher false positive proportion in there or not, but it's quite an interesting factor to note as well. And if we take this sample, we can start with various things. I said before that the host star metallicity of desert planets was starting to show interesting trends and look more like the hot Jupiters. That previously in the Dietel paper was done with 4 planets. We've now got 34, and it very strongly matches that conclusion. So I think that is confirming that hot Neptunes have the same metallicity trend as hot Jupiters, i.e. enhanced metallicity. They don't match the hot Earths in a control sample there. So that's quite a nice result. These things are starting to show that maybe they're showing the same formation patterns as hot Jupiters. Maybe they start in similar environments. Maybe some element of the process is the same. What else can we do? And this is where it gets nice and interesting. We ran all of these 34 planets through the ghastly code, which came out a few weeks ago, is a new atmosphere modeling using some very simple, but still useful core and envelope interior structure modeling. So rather than the complicated 3-4 layer type things, which we didn't really have the information to, we did a very simple 2-layer, just core and envelope, but we did it uniformly across this whole sample, meaning that we can get envelope mass fractions for the entire thing and see what comes out of that. And with that, we find a very striking sort of bimodal population. Now, if you split the population of our planets at an equilibrium temperature of about 1300 Kelvin, which translates to 3 to 4 days orbital period, give or take, you end up with planets interior to that having very low envelope mass fractions uniformly in the sample, less than a few percent. So these are high mass, rocky, dense planets, and that fits what we saw already. The handful that were known before were, like I said, 30 Earth masses, 50 Earth masses, 70 Earth masses with the size of Neptune. These are very dense objects. But even the ones that are less striking than that are showing this low envelope mass fraction. Outside of that, we start seeing a much more diverse population. And I don't show it in this because I ran out of space in the talk, but if you plot planet mass against that envelope mass fraction, they start to correlate. Higher planet masses give you higher envelope mass fractions, but only for the ones colder than this threshold or at a longer orbital period. And that's what we expect for normal planet formation. Higher mass, you can attract more gas, you build up a bigger envelope. So we've got this bimodal population coming up. Now, conveniently, this almost exactly matches the location of that Neptune pileup ridge that I showed right at the start. And we found this before the ridge was even published or I knew about it, so it wasn't even following on from that. So I think there's a lot of evidence building up here that there's a population that kicks off at about 3 to 4 days and inwards in terms of these hot Neptunes. I don't know why they're there yet or how they form exactly, but there's a big open question there, and we're starting to build up a lot of observational evidence about it. Now, if I plot those planets on top of that desert ridge plot, and apologies for the changing colors and the slightly awkward transparency, I did this quite quickly 2 days ago because the ridge thing was coming out recently. And you can see that we're starting to populate this ridge and outside of it region, and they're showing us these more normal planets. Inside of it, even crossing over the boundary that's there, so showing those boundaries are still a bit in flux, but inside of it and in these size regions, we're getting these low envelope mass fractions throughout. Now, if I look at the eccentricity, just to follow on, because we have that, because these are radial velocities as well, it's much less clean. You can't really say anything critical about this. The planets on the inside are showing eccentricities consistent with 0 in all cases, but the noise is a bit high on all of this, and the precision isn't really good enough and could be better. But it does match the general background planet population that you can see there in gray. Now, to summarize all of that, what have we actually got out of this? We've got a defined sample of planets in mass and radius, chosen principled and all in this Neptunian desert region or near it. We've got a confirmation of the host star metallicity showing enhancements, matching the hot Jupiter pattern, done with a much larger sample than previously. We've got some very strong indications of 2 populations turning up in envelope mass fraction. Now, that could mean that photoevaporation is causing this deep desert region. It's removing all the volatiles, and just what we're seeing is the high mass remnants of whatever's left. That depends a lot on when they got there, and I think information on stellar ages will be really important to narrow that down. It could mean some other things. You can add in more exotic scenarios involving collisions blasting off the volatile envelopes and lots of stuff. So you can get quite fun there if you want to push it. I don't think anyone knows the final answer yet, but it's certainly an interesting question. But it seems to be connecting to this pileup of planets at 3 to 4 days as well. So there's another indication of interesting population effects going on there. Overall, I think it's still a very open question, but there's starting to be links to this hot Jupiter formation, but then it diverges at some point clearly. Somehow these planetary cores are getting much higher mass than we thought they should be, and then they're managing to stay there. Now, is it that those cores just exist across and it's only in the desert that they're exposed that we can see them, or is it that they preferentially get put there? We don't really know yet. And so I'll leave it with all those open questions. Thank you.
All right, as a reminder, when you ask your question, name an institution. And I see we have one on this side here. Yeah.
Luke Baumann from Caltech, wonderful talk. What are the constraints on multiplicity right now? In other words, planetary multiplicity. Are there evidence for companions?
Excellent question. Don't have the numbers off the top of my head. Many of the known ones are solo planets, but I wouldn't want to stick myself to that right now without checking it properly. I think it's something that's well worth investigating, especially for much more distant planets. So you can see whether there are Jupiters on wider orbits and if they influence the migration and that kind of thing. That's definitely something we want to look into.
Oh, I see one up there.
I guess this is more of a comment question. The DTARPS project, for which there are two posters out there, has many dozens of new candidate hot Neptunes from a different statistical method. So it'd be very interesting to follow up on those and see if they're similar to the TOI sample that you have studied.
Yes, thanks. And I think one of the early ways to do that would be to try and look at them all in the Hertzsprung-Russell diagram and just look at the stellar types involved. Could be a really early way to try and see whether they're coming from the similar populations or not.
Very good suggestion.
So I actually had a question. The slide's gone now, but you had one of those dense Neptune things that was less than a 2-day period, had pretty high eccentricity. I'm wondering, is that something where you think it's an orbit that's evolving, or does it seem to be stable in that orbit, or is that something it's too soon to say?
So if I'm remembering the slide correctly, there's a lot of noise on that eccentricity, so it's still technically consistent with 0. So I wouldn't want to interpret it too much at this point.
Okay, all right.
Yeah.
Thanks. All right, we have time for one more question. There's one here in the front.
Hi, Brandon Radzim from Indiana University. Great talk. I had kind of a similar question to the first one. Do you know anything about, is there any data for the stellar obliquities for these systems? Because that might be interesting to look at, or any plans to follow them up with stellar obliquity measurements?
Yep, so there's the ATRA-EDS program on Espresso, which is currently targeting Neptunes to do obliquity measurements for basically the exact reasons. So yes, it's not me leading that, that's Vincent Burrier in Geneva. But there's a definite effort to do that. And I think the more of them that get obliquity measurements, the better.
All right, thank you so much. And again, leftover questions to the Slack. One more round of applause for our last speaker.
Okay, so hi everyone. I'm Emma Nabbie. I'm a final year PhD student at the University of Southern Queensland. And today I'll be talking to you, once the slides come up, about the transit timing variations of TESS multi-planet systems and the catalog that I've been compiling using data from the first 5 years. And this catalog will tell us about the frequency of systems at different resonances in TESS. And so we want to do this because if we look at the multi-planet systems from Kepler and we map out the distribution of their period ratios, and I'm defining them such that they are between neighboring planets and always greater than 1, we can see that there's a pileup around the 3:2 resonance, but we don't know if this pileup is being caused by planets coincidentally or if this is actually a feature of their formation. And this is important because, as Juliette established, resonant systems can be a signature of disk migration. And in particular, which resonance a planet is in can tell you things about how that disk migration proceeded. And so this has been a subject of many different theoretical studies, and I encourage you to take a look at them after this. But I will be stepping through a little bit using a set of simulation results from Wang and G. And so if we take, for example, the migration speed on the left-hand plot here, we can see the fraction of different systems that are created at different resonances. And so if we take, for example, the 2:1 resonance, we can see that even at slower migration speeds, we're still favorable to form systems in 2:1 resonances. Whereas in contrast in the white, if we show the 3:2 resonances, it actually takes faster migration speeds in order to create more favorable conditions to form 3:2 resonances. And if we take a look at the stellar accretion rate, faster accretion rates will be more likely to form 2:1 resonances, whereas you need slower stellar accretion rates to form the 3:2 resonances. And this basically supports the idea that you will encounter the 2:1 resonance first, and then you need to be broken out of that and then continue to migrate and encounter the 3:2 resonance. And so 2:1 resonances typically are products of earlier stages of migration, whereas you need faster migration speeds and longer disk lifetimes to facilitate the creation of planets in 3:2 resonances. But it's not enough to just collect data and find planets that are coincidentally near a period ratio resonance. You actually need to see, are these planets genuinely in resonance? And so you need to look at their dynamics. So transit timing variations, or TTVs, are a great tool to do this. They are signatures of gravitational interactions between planets, and they cause non-periodic motion because they push and pull each other to speed them up or slow them down in their orbits. So we can take an example here of KOI 142, and on the x-axis you have the transit epoch, and on the y-axis you have the TTV signal. And you can see these periodic signals of early and late transits. So if we again take the Kepler distribution, but now we only look at those with transit timing variations, interesting features emerge. We can see that there are different fractions of planets at different resonances. However, there are some peaks on this plot that disk migration alone can't explain. And so this is why we need to have more empirical evidence of systems in resonance across a wide variety of planet pairs. So this is where TESS comes in. TESS offers a different perspective in two main regimes, the first of which being orbital resonance. So you can see that instead there are a pileup of planets around the 2-to-1 resonance rather than the 3-to-2 resonance with Kepler. And this can indicate different migration histories than the Kepler planets. And then TESS also extends out to greater mass ratios because there are greater radius ratios between the planet pairs. And this is particularly important because if we look at the Kepler distribution of neighboring radius ratio of these planets, we can see that most planet pairs are actually pretty similar in size and therefore similar in mass. And this paints a picture of the classic Kepler TTV system, which is a system with planet pairs around a 3-to-2 resonance and of roughly the same size and mass. So if we can do a systematic search of TESS TTV systems, we'll be able to get a wider variety of planet pairs and better understand systems in resonance. And so this is what I'm conducting. I have a total of 175 multi-TOI systems in total. And for the purposes of this talk, I will only be focusing on the 20 systems with at least one giant planet, because these are different from the classic Kepler TTV system. However, I do note that there are around 30 systems hosting smaller planets within 5% of the 2-to-1 resonance. And we expect that a number of these will have TTVs, so these will provide a more direct comparison to the Kepler sample. And so we find that out of the 20 systems with giant planets, around 7 of these systems host planets with measurable TTVs. So this is around 35%. And we can see from the radius ratio diagram that we have TTV systems at larger radius ratios and therefore larger mass ratios, which is what we expect. We also find, of course, another peak at the around the planet pairs that are pretty similar to each other. And we also see another pileup at the 2-to-1 resonance rather than the 3-to-2 resonance. Now, I just wanted to show some results of the systems with the most significant TTVs. So we have the TTVs of the TOI 1130 system on the left and the TTVs of the TOI 216 system on the right. And I'd like to just point out the large scales on the y-axis here. So this is basically showing that the inner planets have, or outer planets have slightly smaller amplitude TTVs, but still on the order of several hours. And this is basically just scaling with the masses of these planets. The reason why these systems also have kind of different TTVs is because TESS could really sample a lot of the super period of the TTVs of TOI 216, whereas ground-based follow-up is needed to better sample the TTVs of the TOI 1130 system. We also have the TTVs of TOI 2525. And again, TTVs are a signature of planets in resonance, but also near resonance. So TOI 2525 isn't necessarily in a resonance, but it's near enough to show still these quite strong TTVs. And the plot on the right is an unpublished result that I found through my work. It is the TTVs of the giant planet in the TOI 4504 system. This is actually a planet on an 82-day period orbit, and it has around 40-hour TTVs. And the only other known planet in the system is a super Earth at around an orbital period of a handful of days. So this is not being caused by a super Earth. There has to be another planet that's non-transiting in the system. So that's a pretty cool result. And again, what's really important is characterizing the architectures of these systems through follow-up. And this is easily facilitated with TESS because all of these systems are going to be around brighter stars. And so this catalog is the first step in really having a resource to do follow-up, not only for more precise TTV measurements, but to find other non-transiting planets or better characterize the system's architecture. This is also exemplified with TOI 1130, which is an upcoming JWST target. So the presence of this planet's TTVs basically constrains its formation pathway. So this plot here is a simulation of the data. It's actually going to be taken pretty soon. And so we want to investigate parameters of the atmospheres of these planets and compare them to each other so we can determine their relative locations in the disk where they formed. We also revisit some old Kepler systems. So through the TTVs of KOI 134, which you can see here, these are the transit light curves of a giant planet, which is the lone transiting planet in a system. It was, so these 20-hour TTVs that you can see here are actually indicative of a non-transiting companion in the system. And this is different from the classic Kepler TTV systems because we actually find that the two planets are in a 2-to-1 resonance with an 18-degree mutual inclination. And we also find that KOI 134b, as I'm calling the transiting giant, only transits for about 20% of its lifetime. So the dynamical interactions between these two planets will actually cause the orbit of KOI 134b to be pulled up such that it will no longer be visible. So this is a very serendipitous result. And through looking at the TTVs of the system, we're able to actually find more systems that challenge planet formation theories. And therefore, if we extend this with TESS, we're able to see that we will get a better understanding of systems in a resonance. And so we find that out of the systems with multiple TOIs that have at least one giant planet, 35% of them do show TTVs. And this catalog provides not only a complement to the Kepler TTV catalogs because of TESS's more diverse planet population and because of the brighter host stars that TESS typically finds planets around, we're able to complement and provide direct comparison to similar works that are done with Kepler. And so I will end there, and I'm happy to take questions.
We have time for some questions.
Aviv from the Weizmann Institute. Here. A question about the populations, not necessarily dynamics. You said that the planets are dissimilar. You chose the planets to be dissimilar, which is different from the Kepler view. Back in the day, Laura and Weiss told us that planets are like peas in the pod. Within each system, they are relatively similar. So you say this is actually the peas in the pod phenomena is a byproduct of the way that Kepler chose its targets, and TESS is more uniform, so you actually get very dissimilar planets?
Emma, can you please succinctly summarize that question? Because it's hard to hear them.
Sure. So the question was basically referring to the peas in a pod notion that a lot of the Kepler systems have planets that are very similar to each other, and does TESS kind of disrupt that? So I would say I am not speaking on that in terms of like the absolutes, because TESS has a lot of biases that we are not addressing. This study is a first step in providing observational evidence to answer this question, but there needs to be future work done to address the biases in Kepler, TESS, and just the transit data that we're getting, and actually do population synthesis to see the absolute fractions of systems with TTVs and at different resonances. So I'm definitely not saying that the peas in a pod theory is challenged with TESS. This is just kind of, we are finding differences with TESS, but there are also biases that we are not accounting for in this.
Okay, thanks. Other questions? While we're waiting, I had a question on KOI 134.
Yeah.
What did you mean it's not going to be visible? The transits won't be visible?
Yeah. So first of all, if anyone has any questions about KOI 134, please come ask me. I'd be happy to talk about it. So what's happening is that we are finding measurable transit duration variations of KOI 134. And so this is because not only is the eccentricity changing, but the actual inclination of the planet is changing. So what's happening is that at the planet's orbital period, its inclination is being pulled up above the limit of what geometrically you would be able to see as a transit. So it's basically being pulled up that from our line of sight, it will no longer be transiting.
We have another question right here. 2 questions. We'll take those 2 and then we'll move on. And is Sam Quinn here? Because you're up next.
Thanks. Daniel Bayless, University of Warwick. Thanks for the talk. I was just wondering, you're talking about measurable TTV values. At some level, all of the multi-systems will have a TTV. So what precision are you getting for TESS in terms of TTVs? And are you affected by the change in cadence as we go through different years? Are you affected by the change in data product cadence in terms of how accurately you measure your TTV?
Yeah, so we are trying to use the shortest cadence possible, but there's going to be a trade-off between time resolution and photometric resolution as well. So with TESS, you're typically going to get a per point precision of around 30 minutes. Of course, with giant planets, we're able to find TTVs on the order of a few minutes, but with smaller planets, they need to be on the order of several tens of minutes to like hours. So yeah, that's kind of, it really depends on the transit depth. It depends on, the strength of the TTV amplitudes, but yeah, typically tens of minutes is what we're getting.
Okay, thank you. Last question.
Hi, I'll be really fast. I'm Chris Lindsay. I'm from Yale. I'm just wondering, does the strength or the amplitude of the transit timing variation depend strongly on what type of resonance you may or may not be in?
So yes, to a degree, but it's going to depend on your proximity to a first order resonance. So if you have 3 to 2, 2 to 1, 4 to 3, those are the most likely to produce very strong TTVs and how close you are to them. So I wouldn't say that a 3 to 2 resonance produces stronger TTVs than a 2 to 1 because they're both close to a first order resonance.
Let's thank Emma for her talk and Q&A. Next, we're going to welcome Sam Quinn. He is standing in for Joey Rodriguez. Same talk, though.
Thanks, Sarah. Yeah, Joey has a ruptured eardrum and couldn't fly to the conference. So I'm going to step in and give his talk. This is a project we've worked on together for a while now. Some of you may have seen him give a version of this talk at Extreme Solar Systems. So I'll try to change it up a little bit. But I'll also do my best to be Joey. I didn't have a song to walk into for this conference, so you'll have to bear with me. It's going to be a little less exciting. Okay. So I was fortunate enough to have Juliette Becker give a little introduction to giant planet migration this morning. So if you were paying attention, you would have heard that there are effectively 3 broad categories of giant planet migration that result in hot Jupiters. One would be in situ formation, so no migration. Another dynamically cold situation, so not a lot of sort of violent dynamical interactions, includes migration through the gas disk, formation beyond the ice lines, and then migration inward gently, typically preserving circular orbits and probably the stellar obliquity will remain as it was at formation. Whether that means a disk could be tilted or not is another question. And these are opposed to dynamically hot processes. So these are multi-body interactions of a number of sorts that typically result in require a high eccentricity to bring the planet close to the host star, at which point it can be tidally circularized. So the question is, if these processes all produce hot Jupiters with roughly, broadly the same properties, then how do we decode the secrets of hot Jupiter migration? And the answer is you need a tool that will help you interpret the properties that we observe, the fine details of the properties we observe, and link them together back to their formation mechanisms. So I mentioned a couple of these already. The obliquities and eccentricities might be expected to be excited by these dynamically hot processes, multi-body interactions, but then subsequently modified by tidal interaction. Orbital architectures provide another clue. If you have distant massive companions, those may be the smoking guns for certain forms of high eccentricity migration. But if you have a situation with a hot Jupiter and a nearby small planet, it seems to preclude the high eccentricity migrations because you would expect those small planets to be disrupted, the orbits of those planets to be disrupted. So that may point to an in situ formation or something, a formation closer to the orbits in which we observe them. Another opportunity is to look at the atmospheric composition of these hot Jupiters. And we just heard from Emma that there's going to be some observations of the TOI 1130 system, which is really exciting with JWST. That's an example of a hot Jupiter with a small inner planet nearby. The idea with these types of observations is that for example, the C to O ratio varies across the protoplanetary disk as you move farther away from the star, and you cross various ice lines that sequesters different elements into solids. And so the gas that's accreted by the forming giant planet has different composition. So depending on the location in the disk where those planets form, you would expect a different C to O ratio. Here's a plot from Karin Oberg from over a decade ago now that shows this idea, where you can see that the gases are expected to, beyond, for example, if you get beyond the water ice line, then you have oxygen sequestered in solids, and so the C to O ratio of the gases increases. So if you follow this traditional picture of giant planet formation, you'd expect a high C to O ratio for these objects that form far from the star, whereas something that forms in situ might have a lower C to O ratio. Now, there's a lot of uncertainty in that and questions of mixing inside the planet, inside the disk. Midplane of the disk is going to have different properties than more vertically, more elevated parts of the disk. So what we really want is a way to anchor these predictions with observations. So if we can identify a population of planets where we know what the birth environment was, or at least strongly suspect, then we can start to link these observed properties together and learn more about hot Jupiter formation. I just want to note really briefly that there's other work going on in our groups about these other markers of hot Jupiter migration. So I encourage you to check out Jack's poster talking about new discoveries to help get at some of these eccentricity and obliquity questions, and Branham's poster introducing a project that we've been working on to homogeneously reanalyze the known hot Jupiter population to try and get rid of some of these assumptions that Juliette mentioned this morning that introduce some bias and some systematic noise. But going back to this idea of a sample where we know the birth environment, or we think we know the birth environment. Juliette this morning mentioned these giant planets, hot Jupiters with close friends. We know that most hot Jupiters are what we'd call lonely. They don't have close friends, no close small planets. But some of them, this WASP-47 is sort of the poster child for this class of planet. They do. WASP-47e is an interior planet, so with a period of 0.79 days. The hot Jupiter, WASP-47b, a period of 4 days, and then some outer planets as well. Before TESS, there were a couple of examples of this, but more recently, TESS has discovered several other examples, both new systems and small planets in known hot Jupiter systems. So Our work here is confirming and characterizing two new such systems, TUI 2494 and 5143. And here I'm showing the TESS light curves, raw, flattened, and then phase folded. We have, you notice the scale is different on the blue points compared to the orange points. This is a shallow transit of a mini Neptune, about 2.5 Earth radii, in both cases, about 2.5 Earth radii, and a giant planet at a wider separation. Both small planets have orbital periods of about 2.4 days, just by coincidence. And the host stars are pretty similar too, early G stars. We got follow-up radio velocities in collaboration with many other groups working within the TESS follow-up observing program. And TUI 2494C, the giant planet, is less massive than TUI 5143, but we did get good detections of both systems, and we don't detect the radial velocity motion due to the small planets. We don't have the data for that, but there are other groups who are working on that as we speak. I'm not going to spend much time on this except to note that if you go back to the transits, you might notice that they're kind of V-shaped for the giant planets, indicative of a near grazing or grazing orientation. And you can see that the derived radius, the formally derived radius here for TUI 5143C has huge error bars and is probably unphysically large. That's because it's grazing and we can't actually get a good measurement of the radius. But it does kind of raise the question, what are the inclinations, the orbital inclinations of these planets? Is this typical? Is this what we might expect to see grazing, multiple grazing hot Jupiters? So we took a look at the mutual inclinations, or at least the inclinations as we can measure them from transits of the known systems with small inner planets. And there's a degeneracy there because we don't know from transits if they transit on the same hemisphere of the star or on different hemispheres. So there's some additional uncertainty there. But if we calculate the mutual inclination distribution, so solid line makes no assumptions about transits on the same hemisphere, whereas the dotted line assumes they transit on the same hemisphere, maybe artificially imposing a more well-aligned system. Then we see that the mode of the mutual inclination, projected mutual inclination here, is about 2 to 3 degrees. This is very preliminary, and you can see it's a small sample, so I wouldn't draw too many conclusions about this. But it's interesting that this is similar to the Kepler small planet multis in 2-planet systems. Higher multiplicity systems tend to be flatter, and I think there was a paper by Sarah Milholland, who's somewhere in the audience, a few years back, finding a correlation with the multiplicity and the flatness of the system. So 2-planet systems tend to have short period. 2-planet systems from Kepler tend to have mutual inclinations around 3 degrees. So it's interesting that these share that property with these small planet systems that most likely formed pretty near their observed locations. But we like something a little more certain here. So if we look at the architectures as a whole, this is a plot from Li Zhou Sha's paper on the TUI 2000 system. Then we've got these hot Jupiters in orange and some warm Jupiters just divided at a 10-day orbital period. And it sure looks like they're part of the same population. So interestingly, if we can learn something about these hot Jupiter systems with small inner companions, which are more amenable in some cases to follow-up observation than their warm Jupiter counterparts, maybe we learn something about the warm Jupiters as well, if these really are part of the same population. These are just a short period tail. But more importantly, these systems, because they have these inner planets, which seems to preclude formation via high eccentricity migration, these should comprise a sample that were formed inside the water ice line, and therefore have a C to O ratio that would be expected to be lower. So this gives us that sample that we're looking for with known birth location that we can then observe. This is zoomed in on that. I'll skip over it. So I just want to end with a summary of our findings. We present these 2 new hot Jupiters with inner companions, adding to the growing population that TESS has provided for us. because they've likely formed inside the water ice line, we have a prediction about what the C to O ratio is. And so if we can make observations of these, for example, with James Webb, like we heard is happening for TOI 1130, then we can start to have a benchmark for what we actually expect. If the predictions are consistent with our observations, that's great. If not, then we can go back to modify our predictions or interpret what that means. And then this provides a benchmark for atmospheric characteristics of giant planets for which we do not know the formation location. So most hot Jupiters, you observe their atmospheres, you don't know, you can't link that back to a formation location. But if we have this benchmark, then we can say, the C to O ratios for all of these systems that formed in situ or inside the water ice line are consistent with predictions. And now we have new observations of these planets where we don't know where they formed, and they match. So these particular systems likely formed inside the ice line, or they don't. But either way, I expect that observations of these systems will provide us a lot of new information and interesting results to mull over. Finally, Joey had like a Toy Story, you got a friend in me theme at the exoplanet, at the extreme solar systems. And I think there was some wise guy in the audience who asked about who's who in this woody buzz. So just to put that to rest, I think it's clear based on the height difference. I'll end it there, and thank you for listening.
Thank you. We have time for a couple of quick questions.
Hi, Gijs Mulders, UII Chile. I had a question about the mutual inclinations, which is a very interesting result. So it might be that you miss some systems because they are too mutually inclined. So can you make an estimate of how many of these systems there are that you would have missed? And is it like actually a lot of them more, or is it only a couple that you think you miss?
So I didn't get all the words, but I think I got the gist of it. What about the systems that are more mutually inclined than these, and we wouldn't observe them because they don't both transit? Well, that makes it hard to compare, for example, the mutual inclination distribution of these versus warm Jupiters, because as you expand the orbits, then these same inclinations wouldn't transit as warm Jupiters. But if we want to make the comparison to a population of short period small planets, as I sort of hinted at here, then we're comparing the right semi-major axis range, so that's sort of a one-to-one comparison. Now, it's also an interesting question, is sort of what I think in my back of my mind is what's the occurrence rate of these things, because how many of these do we miss? That's something that I think the RV surveys are going to have to answer, right? If you go measure the mass of a small planet, how many times do you find anomalously large RV variation that could be due to one of these? I think the answer is a pretty small number, but it's an interesting thing to consider, and I think somebody should be doing it.
Agreed. Thanks.
Okay, let's thank Sam again, and thank you. Next, we have another scheduled change. Ashley Chontos was supposed to speak now. She's been moved to Friday. So here we're going to welcome Noah Vowell.
Okay. Can wait a second till my slides come up, but yes, I'm Noah. I'm a graduate student at Michigan State University and a predoctoral fellow at the Smithsonian Astrophysical Observatory. And I will hopefully tell you about some transiting brown dwarf science, but it seems like there are some technical difficulties. I swear I uploaded them. Sure. Yeah, that's probably a good idea. Yeah, so a little bit of background on brown dwarfs. These are traditionally defined as the things that occupy the region in mass between planets and stars. So traditionally, This means about 13 to 80 times the mass of Jupiter. I do need a clicker, don't I? This one. Yeah, there we go. Yeah, so this translates to about 13 to 80 times the mass of Jupiter, where these limits are placed based on where we understand fusion to occur. So less than 13 Jupiter masses, we don't see fusion in theory. And at 13 Jupiter masses, we ignite deuterium fusion, you're a brown dwarf. And then at 80 Jupiter masses, you ignite hydrogen fusion and become a star. Now, more updated models, these transitions are a lot more blurry. In reality, it's something closer to 11 to 16 Jupiter masses for the lower limit. Upper limit's more like somewhere between 70 and 80. And this depends a lot on external factors to the mass, things like the metallicity, for example. But I think it's maybe a little more insightful to think about these objects in terms of how they form and evolve. So on one hand, we have planets, which form in the circumstellar disk, primarily via core accretion. And on the other hand, we have stars, which form via direct collapse or disk fragmentation. This begs the question, what about brown dwarfs? And probably unsurprisingly to many of you, it's probably a mixture of both of these. There is no formation mechanism that we know of that will preferentially form the brown dwarfs. So in reality, what we're looking at is probably the region where these two formation mechanisms for planets and stars are overlapping. And so what I'm really interested in is how exactly do these formation mechanisms overlap, and where might the transition be between planet and star formation? So this leads to a couple key questions that I hope to at least inform you all about. The first just being, how big can a planet be? Relatively simple question, but it's hard to answer. Core accretion theory, at least, says that we can probably form objects well into the brown dwarf regime, but is there any observational evidence for that? In particular, can we actually differentiate between planet and star formation in the brown dwarf regime? I would argue on an individual system basis, this is almost impossible to do, at least for all systems. But as we start to build up a population of more and more systems, we might be able to observe some trends that could tell us where this transition might happen. And of course, this is a TESS conference, so I'm going to talk a little bit about what insights the transiting brown dwarf population provides us that TESS is building. So before that, though, I should do a little bit of history and say that there is this study from 2014 that did something about the statistical properties of brown dwarfs with some implications for different formation mechanisms. Sounds exactly like what I've been talking about, and maybe my thesis was already finished 10 years ago. But I wouldn't be up here if that were true. So a couple quick caveats. This study was from 2014, so this focused primarily on radial velocity discovered systems. I think there were a couple eclipsing, but by and large, these were the radial velocity sample where we don't understand the radius and we don't understand the precise masses of these systems because we're stuck in that mass and inclination degenerate space. But I can quickly summarize some of their findings. Firstly, on short period orbits, they found a deficit of brown dwarfs around 42 Jupiter masses. And if you divide the population there, everything below 42 Jupiter masses appears to be, or appears to have an eccentricity distribution that looks consistent with massive planets. And then the higher mass systems, on the other hand, these authors argue is maybe more consistent with stars. The evidence for that is entirely qualitative in this paper, at least, and summed up in these two plots. On the left is the cumulative distribution function of long and short period brown dwarfs, and we do indeed see a pretty noticeable depleted region around 42 Jupiter masses. And then on the right, as a function of mass and eccentricity, we notice the eccentricity tends to decrease until that 42 Jupiter mass hypothetical cutoff, and then the eccentricity sort of expands again and is much wider. And so this is largely where we sort of stood. The authors have argued that this is indicative of a 42 Jupiter mass transition point, but the this is 10 years later, and we're now in the era of Kepler and TESS. So we have a new perspective. We have over 50 systems of brown dwarf companions that transit their host star. And over 2/3 of these have been discovered or have contributing observations from TESS. And with the work that I'm going to show you here, we're increasing the population by nearly 15% just from this work alone. So a quick aside on how we're finding these systems. It's a relatively standard exoplanet discovery template. So we see transits in TESS. These objects come out as TOIs. They have roughly a Jupiter radius. We get follow-up through the various TFOP working group programs, light curves from the ground, high-resolution imaging, radial velocities, and then we go after more targeted radial velocities, in our case, primarily from the trace instrument, in order to constrain the mass and the eccentricity of these systems. And for the work that I'm showing you here, we'll have done that for 12 new TOI systems. So let's take a look. I'm showing you just a mass radius plot for transiting companions from 7 up to 150 Jupiter masses. And so you can see the systems we're contributing, at least as the dark purple diamonds. We have 6 new transiting brown dwarfs, 6 new very low mass stars, and I have some convenient dotted lines to show you the canonical 13 and 80 Jupiter mass cutoffs. And one interesting thing to note here is that we don't actually see any observable transition in radius, at least, as you cross these boundaries. But one thing we do notice, similarly to the 2014 study, is that there is some deficit of brown dwarf systems. In our case, it seems to be at a bit lower mass, maybe around 30 Jupiter masses when compared to the 2014 study. But qualitatively, at least, we are seeing something similar. And so we can also look at the eccentricity to see if we're seeing some of the same trends. And in fact, this is what a lot of transiting brown dwarf work has looked at in recent years. This plot comes up a lot, and at face value, you might say that we're seeing something similar. The low mass systems do, at first glance, appear to be lower eccentricity than the distribution of higher mass systems, but I'm up here hopefully to convince you that it's probably a lot more complicated than this. Mostly because if you want to consider what's going to primarily govern your eccentricity evolution, it's not necessarily the companion mass, but more likely the mass ratio of the system. And so if you make this same plot in mass ratio and add in some super Jupiters and some definitive low mass stars, you would expect to see at least the same sort of dichotomy, if not even more amplified. But in fact, we see the exact opposite. There doesn't appear to be any noticeable difference between these two populations. Here, the vertical line is just a 42 Jupiter mass companion around a sun-like star. And yeah, we don't see any difference between low mass ratio or lower mass systems versus the higher mass systems. So I would argue for the transiting systems, at least, it seems to be much more complicated than just the eccentricity distribution. But hope isn't lost. We have other parameters that we can look at to try and distinguish between different formation mechanisms. And again, we can look to a little bit of history for some inspiration. In particular, there's this landmark result from Fisher and Valenti in 2005 that found that stars that host planets tend to be more metal rich than their volume limited sample. So this is the plot right here, where the stars that host planets is the sort of dashed dotted line. It's maybe a little hard to see, but you can take my word for it that it is more metal rich than the volume limited sample. And so if we want to apply this to brown dwarfs and just sort of assume the same 42 Jupiter mass cutoff just to test, we can look at the high mass brown dwarfs versus the low mass brown dwarfs and see if the ones that are low mass are forming like planets, then you might expect that these guys will have a more metal-rich host star distribution. And at first glance, maybe this is, maybe this is what we're seeing. I hesitate to hang my hat on this, but these histograms don't look exactly the same. But there's a lot going on under here that I'm not sort of addressing. Most notably being that these metallicities are all measured completely heterogeneously. These are just drawn from the, these are just drawn straight from the literature. So a variety of different spectrographs, a variety of different pipelines, techniques have gone into measuring all of these. The way you would want to do this sort of more robustly is to have a survey of transiting brown dwarf host stars, and all with the same spectrograph, analyze them the exact same way. And hopefully in a few years, I'll be able to show you more on that. But at least as of right now, this seems like maybe a promising avenue to pursue. So some conclusions. TESS is continuing to pump out transiting brown dwarfs at an increasing rate. We are just now above 50 systems with many, many more to come. We have no signs of slowing down. In terms of this question about planet versus stellar formation and where they might transition, there's no clear evidence in the transiting systems, at least, for this 42 Jupiter mass cutoff in the eccentricity distribution. Metallicity seems like a promising avenue to pursue, but it requires a much more careful approach that hopefully in the coming years I can tell you a little bit more about. But that is all. Thank you.
Interesting talk, Eric Gaius, University of Hawaii. What about spin orbit alignment?
That's a very good question. So yeah, there's been a lot of interesting work in giant planets showing that spin orbit alignment does seem to have some correlation, at least with migration pathways. And I do think this is a really promising avenue for transiting brown dwarfs. But only, I believe, 4 or 5 have been published so far. And in terms of obliquities for transiting brown dwarfs, I know of a handful that have yet to come out, with I think close to half a dozen to a dozen with proposals this year. So it's definitely something that we're interested in pursuing and are pursuing, but there's not enough data yet.
Other questions? You're in the front.
Hi, Ling Hao Ma from Princeton. Thanks for the great talk. So what about the possible correlations of eccentricity versus the stellar properties like temperature or?
Sorry, can you repeat that?
So what about the correlations between this eccentricity of brown dwarfs and the host star properties like temperatures or whatever, anything? Yeah.
Sorry. Yeah, I think the eccentricity distribution is not necessarily indicative of this 42 Jupiter mass transition. In terms of the host star properties, there's many other things that we can consider. Specifically with the obliquity distribution, using that as a function of host star temperature will be really interesting. Seeing how things transition across the craft break. But I think it's probably too early to say anything about that without more systems.
Okay, thanks.
Okay, we're out of time for questions, so let's thank Noah again. Okay, next up is Elisabeth Newton to tell us about young systems.
Awesome. Thanks, everyone. It's really great to be here. And today I'm going to be talking about
young exoplanets with the motivation of trying to observe planetary evolution. There's a lot of different reasons to do that. We heard some from Juliette Becker this morning. We might also want to study their atmospheres, chemistry, their radius evolution and cooling, atmospheric escape, and then of course dynamical evolution. So how do we do that? So we can take the approach of modeling the population of old planets. This is a picture from JWST. I didn't get a chance to snag the group photo we took this morning, where we can look at all of the exoplanets in the field of the galaxy. So these are stars that have ages about 1 to 10 billion years old. We don't really necessarily know very precisely. And we can learn a lot about exoplanet evolution from studying those. The other approach we can take is to study young exoplanets, which are snapshots in time of planet evolution. The second is the approach that's being taken by our collaboration, the THYME collaboration, which stands for the TESS Hunt for Young and Maturing Exoplanets. And I just wanted to take a moment to put out my greatest appreciation for the many wonderful collaborators that I have in this project, some of whom are here today. So today I'm going to tell you about 3 different aspects. I'll talk about how we determine the ages of stars. I'll demonstrate that through a case study of a particular exoplanet, TOI 2048. And then lastly, we'll take a brief look at the population of young exoplanets. So how do we determine the ages of stars and therefore their planets? I can tell you how old these 2 are. We can ask their parents. But it's going to be a lot harder to get a good answer out of a star about how old it is. Luckily, we do still have some tools at our disposal. 2 of those are rotation and lithium, which are shown here. These both show rotation or lithium as a function of spectral type or one of its proxies. Okay, so with the THYME collaboration, we're looking for planets in young associations specifically, because through our membership with the association, that gives us a good handle on the age of the association, or on the age of the planet. So THYME represents a synergy between exoplanet astronomy and stellar astrophysics, as well as between the TESS mission and the Gaia mission. So we're combining these 2 different aspects in order to learn more about young exoplanets. Our case study, TOI 2048. This exoplanet was discovered in a cluster that was only discovered in 2019, which is called Group X. This young association is relatively sparse on the sky, and it was only discovered when we had this precise data, this precise astrometry from Gaia. So I'm showing here the right ascensions and declinations of this cluster. In pink and lavender are the cluster members from the 2 papers that independently discovered this association. And TOI 2048 itself is marked as the pink star. We also did a search for new stars in this association, and our probable members are shown as those dark yellow circles. So this is the first step to characterizing a young planet. It's identifying the association that it's in, so that we can use this ensemble of stars to learn about the age of the group as a whole, of the host star of TOI 2048 itself, and therefore of the planet as well. All right, so we can use these 2 tools that I mentioned to learn about the age of this association. When we look at these plots, what each of them are showing is a different cluster or association of stars in each of these different colors. This one here from Luke Booma's work is showing rotation as a function of age. And you can see that these populations are gradually increasing with time. So rotation periods are slowing with time due to the spin down of stars. We also see that lithium equivalent width as a function of stellar spectral type is also changing as a function of age, although in a fairly more complicated manner. So the first thing that we did was to use stellar rotation to determine age. So here we have another look at rotation period versus spectral type. Now in the back here, these salmon colored points are stars from the 350 million year old cluster NGC 3532. And in turquoise maybe are the measurements that we made using TESS and ZTF for stars that are in group X. You can see that they line up very well. And from that, we can conclude that group X is the same age as NGC 3532. And that age is about 350 million years, plus or minus 50 years. This was determined for NGC 3532. We can assume it's the same for group X. Next up, we use lithium from ground-based spectra to determine the age of the cluster. So again, shown here, these are the lithium measurements. Now I have two different benchmark clusters, the Hyades and Pleiades, at 120 and 650 million years old. So lithium is decreasing with time. And then the measurements we made are shown here in yellow. You can see that they're bracketed by these two clusters. So we can say that the age is somewhere in between that of the Pleiades and Hyades. That's consistent with our rotation analysis. But we can do one better than that. And that's something that Raina Rampali, who's a graduate student at Dartmouth, she has a talk on Wednesday about something completely different. But she used the spectra and the lithium and measured equivalent widths. She measured the lithium equivalent widths and then used those measurements to determine the age of the cluster. Again, using the whole ensemble of measurements we'd made. So these are the posteriors for each of the individual stars in the dashed lines, and then the ensemble posterior, which is much more precise in the solid line. Raina measured an age of 260 plus or minus about 30 million years. And then lastly, of course, I would probably be remiss if I didn't at least show a plot of the planet. So this is the phase folded light curve of TOI 2048b, which is a 13.5-day period and has a radius of 2.5 Earth radii. And from all of the work that we did to learn about the age of this system, we can say that this planet has an age of about 300 million years with an error of about 15%. So there are a lot of different things that I could talk about with respect to this population that would be totally fun, and I'd love to talk to you about it, but it is almost the end of the day. And so I'm going to focus on just one question, which is how big are these young exoplanets that we're finding? So I'm going to demonstrate that in a non-statistical way by looking at the planet radius versus period diagram. In the back here are Kepler field age planets from Anne Detio's work. Plotted on top here, now these are our older young planets with ages greater than 500 million years. And you can see that they follow pretty much kind of a similar distribution as the field age planets. If we look at the youngest planets, less than 100 million years old, especially those that are less than 100 million years old, we can see that they are, by eye, quite large. So we're finding a lot of really young, puffy young planets. So we have two talks tomorrow. They're both right after lunch by Rachel Fernandez and Sydney Vach about statistics of young exoplanet populations. And so I'm really looking forward to these. And so I hope I'll see all of you all there. For the purposes of my next 3 minutes, I'm going to introduce just two of these planetary systems, the two of the largest ones. So this is HIP 67522, which is 17 million years old, and TOI 1227, that's just 11 million years old. These are some of the youngest and largest planets in our sample. So first, TOI 1227. This is a Jupiter-sized planet, and it orbits a late-type M-dwarf star. That would be unusual. That's not a common type of planet that we have around field-age stars. But James Owens had these great models looking at the radius evolution of this planet, including photoevaporation and, very importantly, the cooling of the planet with time. You can see the current location of the planet, which we can mark there because we do know how old it is. And we can see that over time, this planet is going to shrink and become a much smaller, more typical Neptune-sized planet. Next, I'll look at HIP 67522. And Pachia Tao, who unfortunately couldn't be here, has a wonderful JWST transmission spectrum of this planet. And from that spectrum, she is able to constrain the mass of this planet to be less than 20 Earth masses. So these JWST transmission spectra are shown here. The data is the black points, and the different models showing different masses of planets are shown in the different colored curves. So again, this is an example of a planet that is not a future hot Jupiter. It just looks like it right now. Then finally, the last planet that I wanted to mention is one that you can hear all about from Madison Barber again tomorrow. This is a really exciting planet. It's a giant planet orbiting a 3 million-year-old T-Tauri star that still has a transition disk. And so I'll just leave it at that. Madison's talk is also right after lunch tomorrow. It's clearly going to be a really exciting session. All right, so to wrap that up, our planets in young clusters enable us to measure accurate ages for stars and therefore of their planets. And as an example of this, I've walked us through how we used rotation and lithium in group X to determine the age of the exoplanet TOI 2048. And then finally, looking at the distribution of young planets, we found a lot of cool puffy ones that, thanks to the types of stars that TESS is targeting, are ones that we can follow up and learn quite a lot about. And so with that, I will take questions.
Questions? While we're waiting, I'll ask one. The star with the transmission spectra, these young stars are active, no matter their type, right? Can you comment on the activity, if any, seen in that star?
Yeah, so like all of the young planets, it shows photometric variability and strong magnetic activity in like the UV part of the spectrum. But in terms of the transmission spectrum, Pachia and Andrew have done an analysis of constraining the presence of spots in the spectrum, and it does not seem to be a big deal.
Interesting.
I should add, these are G dwarf, like young G dwarf hosts rather than M dwarfs.
I know, but the young G dwarfs
are also very active. Yeah.
Okay, great. All right, we have a question here.
Hi, Natalia Guerrero, University of Florida. Thank you for this talk, Elisabeth. Have you found, or are you looking for, or how difficult would it be to find other planets in like these really young systems? Like, what do you expect there?
Yeah, so could we find additional planets in these young systems? So definitely yes. We have, in the case of, so at least one of these, we've found a third planet in the system after additional TESS observations. Madison also led that work, and I think she's here, so you should ask her about it. And then, in general, I think, so this is an injection recovery, just an injection recovery example. So the red dots are stars that are injected planets that were not recovered. And so it's certainly harder to find smaller planets. And so we often are skirting the boundary of what's detectable in terms of smaller planets. But I think there is still more to be learned, especially for the ones that haven't had significant additional orbits beyond the discovery, or TESS orbits, cycles beyond discovery terminology. Yeah.
Okay, we do have time for one more question.
Hey, Elisabeth, this is Luke Bauma from Caltech. Where are the young hot Jupiters?
That's a great question. They could be not there yet. That's certainly one possibility if they migrate in later. And they could be there, but super puffy, although I think that they'd run into issues with boil off, potentially depending on how puffy they are, and atmospheric, extreme atmospheric escape at very young ages. So I think that's an excellent question.
Okay, let's thank Elisabeth again. Okay, last up in today's session is Alex Polanski.
Sweet, thank you all. You are superstars for sticking around.
My name is Alex Polanski. I am a no more year grad student at the University of Kansas, about to start my Percival Lowell postdoctoral fellowship at Lowell Observatory. And I am currently in the middle of moving my life across the country, so you'll have to excuse me if I'm a little beholden to my notes for this talk. But just to start, I would like to take some time to highlight that our field is at a really exciting transition point. In the last 2 decades, we've made a massive amount of progress in discovering thousands of other worlds, nearly 6,000 confirmed exoplanets to date. Of course, the lion's share of these discoveries were made possible by transit detection surveys like Kepler, and of course, what we're all here for is TESS. But now that TESS is in its second extended mission and JWST is performing phenomenally, we're really starting to transition from discovering a lot of new worlds to trying to dive deeply into the systems that we already know about. And understanding the architecture of planetary systems is one of the most important avenues for placing these planets, and indeed the planets in our solar system in greater context. The radial velocity method has played a really important role in understanding how exoplanet systems arrange themselves. Because it's one of the oldest detection methods, we now have RV datasets that span nearly a decade or more, enabling the discovery of long period massive planets analogous to that of Jupiter and Saturn. In the last few years, we've also seen the commissioning of new RV instruments that push single measurement precision down to the sub-meter per second level. This new capability means that we can begin to detect even smaller planets on both long and short period orbits, and finally begin to treat stellar activity as the signal that it is and not just a source of noise. And so the combination of new facilities and the maturation of long RV surveys means that we have a lot of massive companions, and we can begin to find smaller terrestrial planets, allowing for more of a fuller picture of the orbital architecture of these systems. And alongside all of this has, of course, been the TESS follow-up observation program. So TFOP has been really crucial at focusing many observing resources, especially the radial velocity resources, on these preferentially brighter TESS discovered systems. And that includes the follow-up effort that I will be talking about today, which is the TSS-Keck survey. So TKS is a NASA strategic mission support program made up of collaborators from multiple different institutions stretching all the way from Hawaii to the Midwest. The idea is to be able to apply for a lot of time on high-res at Keck and the automated planet finder at Lick Observatory, pull that resulting telescope time together, and coordinate observations in order to make the most efficient use of time on these instruments. So the survey itself was started about 3 years ago with a very well thought out target selection process that identified 86 TESS objects of interest that were valuable across multiple different science cases. This work was led by Ashley Shantos, who is now a postdoc at Princeton, was supposed to give a talk before this, but is unfortunately stuck in Newark Airport. But she will be giving that talk about the evolved systems in our survey on Friday. And the ultimate goal of this survey was to measure precise masses for around 100 exoplanets. Nearly half the 86 TOI sample was selected specifically to answer questions about system architecture. And my own work with TKS, in addition to over 50 observing nights on Keck, was essentially the capstone to our survey, which is the TKS mass catalog. So the TKS mass catalog served a number of purposes. The first is that it was our last big planet mass and data release for our survey. In total, we took over 10,000 radial velocity data points spread between all of which will be published in this catalog, including RVs for which we're only able to get an upper limit on the mass. Second of all, this was, we used all this RV data to conduct a very large and uniform fit to each planetary system to obtain mass constraints for 126 planets and candidate signals. This is the largest type of analysis to date. And finally, we used this work as an opportunity to try and discuss how well our survey performed. Did we meet the goals that we set out 4 years ago to achieve? And I want to give a big shout out to the people at the Exoplanet Archive who dealt with the headache of getting this paper ingested into the archive. So thank you so much, Jesse. So while this talk isn't necessarily about mass measurements, I'd be remiss to not show the canonical mass radius diagram. There it is. So here we have the mass radius space for all known planets with some decently precise mass measurements in gray and the TKS sample in blue. So these circles are actually sized according to their mass precision. So the bigger circles actually correspond to a more precise mass measurement. In total, TKS was able to produce mass constraints for 126 planets across nearly this entire parameter space. Now, of course, how well we constrain these masses really does depend on the RV cadence selected, but in total, we were able to obtain a 3 sigma mass constraint for around 74 planets. My own work has helped confirm and validate over 30 new planets, shown here in these gold circles and triangles. And TKS alone was able to nearly meet the TESS level 1 science requirement of 50 small planets with some measured mass. I think we got to around 32. So I'd like to frame the rest of this talk around how TKS has been supporting the investigation into exoplanetary systems through some aspects that the RV observations bring to the table. And 2 that I think are really important in this case are the detection of non-transiting planets and resolving the eccentricity of planetary orbits. So a critical strength of the RV method is, of course, being able to detect planets of the non-transiting variety. This is especially important at increasingly larger separation as the transit probability drops significantly. So here's a little abacus plot showing the systems where we were able to detect additional signals. The points are sized and color-coded according to their mass or their M sin I. So of the 86 TOIs we surveyed, we were able to confidently detect a non-transiting companion in 12 of these systems. Interestingly, these additional planets were found nearly exclusively in systems that only had 1 single transiting planet. While we obviously have to be aware of the varying degree of completeness in our sample, this preference might be explained by the idea that systems with a single transiting planet are really just multi-planet systems, but with a larger spread in their mutual inclination, as we've heard in the session before. This is also seemingly supported by the absence of a certain TOI from this list, which is TOI 1136, which is a very young system of 6 planets in 6 transiting planets in a very stable resonance chain, where we do not detect any additional planets or even indeed a long-term RV trend, which implies that these highly ordered systems are particularly stable against large variations in their mutual inclination. Among our non-transiting planets, many of them are 30 Earth masses or greater, which again would sort of make sense in the context of high mutual inclinations. More massive planets are probably a little more efficient at driving the instabilities that lead to these range of different inclinations that we might see. So the second benefit of RV monitoring is what has piqued my interest lately, is the measurement of the planet's orbital eccentricity. So we have been able to, this is a gallery showing all the planets in the TKS sample where we have been able to confidently measure their orbital eccentricity. It's actually roughly to scale. So at the top, it's kind of hard to see the actual star and indeed the planet. It's just because the actual orbit is actually quite large in comparison. We can see that some of these orbits are nearly circular, but some are fairly elliptical. But I'd like to focus in particular on the systems that host an eccentric sub-Neptune planet. In total, from our analysis, we found 4 sub-Neptunes with a good eccentricity measurement. This is a relatively small sample just because, just like the mass for small planets, the orbital eccentricity for small planets is also quite hard to measure. But making more of these measurements is incredibly important for understanding these planets' formation histories. One interesting idea is that these planets got their non-circular orbits from the presence of yet to be detected giant planets that also orbit that same star. And so I've tried to illustrate that process a little bit here. We start with this very well-ordered planetary system, sort of akin to our own solar system, with tightly packed small inner planets and a long period giant in the outskirts. The giant planet's gravitational influence begins to perturb the orbits of the smaller planets, which will then interact with each other and may result in the complete ejection of some of the smaller planets, leaving potentially one inner sub-Neptune, potentially on an eccentric orbit, and of course the giant planet that caused this mess in the first place. But these giant planets likely have orbital periods on the order of many years. They are very unlikely to transit. So how do we actually find them? Well, of course, radial velocities is probably the answer to that. So even with a survey like TKS that lasts only around 3 years, we can detect possible distant companions just from the fact that radial velocity signals are additive. So if we're looking at a certain star and we measure a certain number of RVs in, say, a year or two, we might detect an upward trend or downward trend, doesn't quite matter. One possibility is that this trend is actually just one small piece of this larger RV curve that we are just sampling for that bit of time. So we might not be able to fully resolve the orbit, but we might be able to infer the existence of another planet in the system. So that sort of begs the question, if I can change the slide, thank you. For our little sample of eccentric sub-Neptunes, do we see any radial velocity trends in our data? So for two systems, we can immediately say no, at least given the sort of 3-ish year baseline of our survey, we don't see any long-term trends. But the story is different for the other two, starting with HD 156141b. We do see an upward trend that even sort of looks curved, even if you squint. It's tempting to say that we found a very, a long period massive companion in the system, but we need to, of course, be careful. The stars that we are studying are not homogeneous gas spheres of gas, but these sort of messes of gas and magnetic fields. So if we look at a similar plot of the S value versus radial velocity, which is just measuring the activity index of the star, we see a very strong correlation between the two. So long period activity cycles in stars is not particularly rare. In our own sun, we see cycles that are on the order of 11 years. And in this case, we're probably seeing some stellar activity and not another planet. So what about the other one, HD 77946b? So here we do see slight evidence of a downward trend in the RVs. It's a bit hard to see here given the scaling, but we do detect it. And just as before, we check to see if the star is doing anything funky. We don't see any correlation between our RVs and the stellar activity indicators. The star does show signs of activity, but they does not seem to be manifesting itself in the RVs that we measure. And so this makes for a really good candidate for a distant companion. Although I should note that this trend is most justified when you include that sort of final tranche of RVs from APF. And so I would really argue that further RV monitoring of the system should be carried out to see if this trend continues. So for our small sample of eccentric planets, we see only some evidence of a distant giant in one. And now this might make sense given the comparative rarity of distant giants, which is around 10%. And so some of these planets are multi-planet systems where, actually I'm going to go ahead and show a eccentricity versus radius plot. And so we're beginning to find more and more an abundance of these eccentric sub-Neptunes. Some of them are in multi-planet systems, which could be exciting these eccentricities, but some are also on orbits less than 10 days. And so maybe their orbits should be tidally circularized in some reasonable time frame, which begs the question, how common are these? So here's a preliminary plot from Greg Gilbert, who is a postdoc at UCLA, who was looking at, and if you would like to hear more about this later, you can absolutely come and talk to me. But I will leave my conclusion slides up here and take questions.
Thank you. Okay, let's go for one or two quick questions. Question back here.
Thanks for a great talk. Tobin Weiner, University of Washington. I was wondering how you handled the degeneracy between eccentricity and inclination and how that kind of factors into some of these models.
Yeah, so there's definitely that. So that's especially true for if you're looking at the eccentricity from, say, the photoeccentric effect, and that's definitely something we would want to look at, especially in Greg Gilbert's work. There's a degeneracy between, as you say, the inclination, but also the impact parameter. Getting more of these RV measured eccentricities, which would be independent of the inclination, would be really important for trying to tease out the distribution for these smaller, for the smaller planets in the eccentricity space. But transit photometry plus RVs would be ideal.
Okay, any other questions? Well, we're standing between the end of the session and the end of the day, so let's thank Alex again for his talk. And